Hello, and welcome to The Gentle Scientist. I'm so glad to have you here tonight. Tonight, we're going to talk about quantum physics. It sounds like something reserved for people in lab coats, for brilliant minds working with incomprehensible mathematics, doesn't it? But tonight, we're not approaching quantum physics as an exam to pass or a mountain to climb. We're approaching it as a bedtime story, as the universe whispering its deepest secrets to you in the quiet hours. Because that's what quantum physics really is, at its heart. It's the universe's most beautiful mystery. The place where reality stops behaving the way we expect it to, where particles can be in two places at once, where separated twins remain connected across vast distances, where the very act of looking at something changes what it is. It sounds like magic, doesn't it? Like something from a fantasy novel. But it's real. It's as real as the device you're holding, which wouldn't work without quantum mechanics. It's as real as the sun that will rise tomorrow, which shines because of quantum tunneling. It's as real as your own body, where quantum effects might be playing out in your cells right now, in this very moment, as you breathe and listen and exist. Richard Feynman, one of the greatest quantum physicists who ever lived, once said, "I think I can safely say that nobody understands quantum mechanics." And he said this after winning the Nobel Prize for his work in quantum physics. Isn't that oddly comforting? Even the experts are mystified. We're all standing together at the edge of understanding, peering into something vast and strange, trying to make sense of it with our limited human brains that evolved to hunt, gather, avoid predators, and navigate a world of medium-sized objects moving at medium speeds. Our brains weren't designed to understand the quantum realm, and yet, here we are, trying anyway. Tonight, we're exploring the lesser-known corners of quantum physics. Not the famous thought experiments you might have heard about, but the deeper oddities. The facts that don't make it into popular science articles. The discoveries that made physicists stop and stare at their data in disbelief. We'll discover how quantum effects aren't locked away in the microscopic world. They're everywhere, including in living things, possibly in you. How empty space isn't empty at all, but seething with particles that pop in and out of existence. How experiments seem to violate our understanding of time itself, where choices made in the present appear to change the past. But we're going to do it gently, like we're turning the pages of a mysterious book together, taking our time with each revelation. The universe has been keeping these secrets for billions of years. We can take our time discovering them. I want to tell you something else, something important. Quantum physics isn't just weird facts about particles. It's a different way of seeing reality. It suggests the universe isn't the solid, predictable, mechanical thing we thought it was. It's fluid, probabilistic, interconnected in ways that defy our everyday experience. Before we begin our journey tonight, I'd love to know, where are you watching from tonight? Take a moment, if you'd like, and leave a comment below. There's something rather beautiful about knowing we're all scattered across this planet, separated by thousands of miles and multiple time zones, yet here we are together, sharing this moment, contemplating the same mysteries. And if you're finding some peace here, I'd be deeply grateful if you'd consider subscribing to this channel. Hit that like button if you're so inclined. Share this with someone who might need a gentle voice in the darkness. It helps more people find their way here, to this small corner of calm we're building together. Now then, take a deep breath. Let your shoulders drop. Feel the weight of the day melt away. For now, just rest in this moment. You're here. You're listening. You're about to discover things about reality that will surprise you, puzzle you, and perhaps, in the end, fill you with a deep and quiet wonder. Are you ready? Let's begin our journey into the quantum world. Back to the late 1800s, to a world of gas-lit laboratories and brass instruments polished to perfection, to an era when gentlemen scientists wore waistcoats and conducted experiments with the precision of watchmakers. This was the golden age of classical physics, and physicists had every reason to feel proud. They had, they believed, figured out the universe. And they had good reason for this confidence. Think about what they'd accomplished. Isaac Newton, 2 centuries earlier, had given them laws of motion and gravitation that explained everything from falling apples to the orbits of planets. You could predict when Halley's Comet would return. You could calculate the tides. You could design bridges and engines and understand the swing of a pendulum. The equations worked. They worked beautifully. Then, in the 1860s, James Clerk Maxwell unified electricity, magnetism, and light into one elegant set of equations. Light, it turned out, was an electromagnetic wave. Radio waves, visible light, ultraviolet radiation, all the same phenomenon at different frequencies. The equations predicted the speed of light from fundamental constants. It was breathtaking. Mathematics and reality dancing together in perfect harmony. Thermodynamics explained heat engines and entropy, telling us why steam engines work and why you can't unscramble an egg. The laws of conservation, energy, momentum, angular momentum, held true in every experiment. The periodic table organized the elements. Spectroscopy revealed what stars were made of. Physics wasn't just working, it was triumphant. The universe, as Victorian physicists understood it, was deterministic. This word is important, so let me explain what it meant to them. Deterministic means that if you know the present state of everything, the position and velocity of every particle in the universe, you can, in principle, calculate the entire future and reconstruct the entire past. Everything that will ever happen is already determined by everything that has happened. The future is just the inevitable consequence of the past, following immutable physical laws like a row of dominoes falling in sequence. This idea was most famously expressed by Pierre-Simon Laplace in 1814. He imagined an intellect vast enough to know the position and velocity of every atom in the universe. This hypothetical being, later called Laplace's demon, could use Newton's laws to predict everything that would ever occur. Every thought you'd ever think, every word you'd ever speak, every choice you'd ever make. All of it already determined, already inevitable, from the moment the universe began. Now, you might think this sounds disturbing. No free will, no genuine randomness, no surprises. Everything predetermined like a movie that's already been filmed, and we're just watching it play out. But Victorian physicists didn't find this disturbing. They found it beautiful, elegant. It meant the universe was fundamentally comprehensible. There were no miracles, no mysteries that couldn't eventually be solved. just mathematics and matter, following rules like a vast cosmic clockwork. The universe was a clock, an enormous, intricate, perfect clock, wound up at the beginning of time, ticking away according to precise mechanical laws. Every gear turning exactly as it must. Every second following inevitably from the one before. It was a comforting vision in its own way. The universe made sense. It could be understood. We were on the verge of knowing everything. In 1900, Lord Kelvin, one of the most distinguished physicists of the age, the man after whom the Kelvin temperature scale is named, gave a famous address. He said that there was nothing new to be discovered in physics now. All that remained was to make measurements more precise, to calculate things to one more decimal place. The great edifice of physics was complete. Oh, there were two small dark clouds on the horizon, he admitted. Two minor problems that needed clearing up. But surely, these were just technical difficulties. Nothing fundamental. He was wrong. Spectacularly, wonderfully wrong. Those two small clouds would become thunderstorms that would completely transform our understanding of reality. One would lead to Einstein's relativity. The other would lead to quantum mechanics. But in 1900, at the turn of the century, these revolutions were just beginning. The cracks in the clockwork were still small enough to ignore. Almost. Let me tell you about one of those cracks, the one that would lead directly to quantum physics. It had to do with something called blackbody radiation. And if that term sounds technical and intimidating, let me make it simple. A blackbody is an idealized object that absorbs all the light that hits it. It doesn't reflect anything. When you heat it up, it glows. Heat it enough, and it starts glowing red. Heat it more, it becomes orange, then yellow, then white. If you could heat it infinitely, classical physics predicted it would glow blue, then ultraviolet, then emit radiation at shorter and shorter wavelengths. The question physicists were trying to answer was this: at any given temperature, what spectrum of light does a blackbody emit? How much red? How much blue? How much ultraviolet? It seemed like a straightforward question. The kind of thing classical physics should handle easily. But when physicists worked out the math using classical assumptions, they got a bizarre result. The equation said that as wavelengths got shorter into the ultraviolet range, the intensity of radiation should increase without limit toward infinity. This meant that every heated object should be emitting infinite energy in ultraviolet light. Your body, heated to 37 degrees Celsius, should be blazing with infinite ultraviolet radiation. A campfire should be emitting infinite energy. Obviously, this doesn't happen. Hot things don't emit infinite energy. They don't destroy the universe with ultraviolet radiation. The predictions of classical physics were absurd. Physicists, with a flair for the dramatic, called this the ultraviolet catastrophe. I love that name. Catastrophe, lurking in the ultraviolet, at the frequencies too high for eyes to see. It sounds like something from a science fiction story, but it was real. Classical physics had failed, and failed completely, at explaining something as simple as the color of heated objects. Scientists tried everything to fix the equations. They tried different assumptions, different approaches. Nothing worked. Well, nothing worked if you insisted on using classical physics. The experimental data was clear. At high frequencies, The intensity of radiation didn't increase to infinity, it dropped off. Black bodies emitted less and less ultraviolet radiation as frequencies got very high. The universe, it seemed, had a mechanism for preventing the ultraviolet catastrophe. But what mechanism? Classical physics offered no answer. And this wasn't the only anomaly piling up in physics laboratories across Europe. There was the photoelectric effect. When light hits metal, it can knock electrons out of the metal. But here's the strange part. Bright red light, no matter how intense, doesn't do this. While even dim violet light does, classical physics said the brightness, the intensity of light should be what matters. More intense light means more energy. But experiments showed that frequency mattered instead. High-frequency light knocked out electrons. Low-frequency light didn't, regardless of how bright it was. Why? No one knew. Then there were atomic spectra. Heat up hydrogen gas and it glows, emitting light. But when you pass that light through a prism and examine the spectrum, you don't see a rainbow. You see discrete lines, specific frequencies of light, and only those frequencies. Every element has its own unique pattern of spectral lines, like a fingerprint. Sodium gives you two yellow lines very close together. Hydrogen gives you a red line, a blue-green line, a deep blue line, a violet line, following a mysterious mathematical pattern that a Swiss schoolteacher named Balmer had worked out empirically in 1885. But why? Why did atoms emit only certain frequencies? Classical physics predicted they should emit a continuous spectrum. The discrete lines made no sense. Actually, even worse, according to classical physics, atoms shouldn't exist at all, because orbiting electrons are accelerating, changing direction as they move in circles around the nucleus. And Maxwell's equations clearly stated that accelerating charged particles must radiate electromagnetic energy, which means orbiting electrons should be constantly losing energy, spiraling inward toward the nucleus like water circling a drain until they crash into the nucleus in about 1/10 of a trillionth of a second. Every atom in the universe should collapse instantly. But here we are, made of stable atoms that have existed for billions of years. Classical physics couldn't explain why we exist. There was also the puzzle of specific heat, how much energy it takes to heat something up. Classical physics predicted that the heat capacity of solids should be constant at all temperatures. But experiments showed that as you cool things down toward absolute zero, their heat capacity drops, approaching zero. Materials become harder and harder to cool further. Why? Classical physics had no answer. These weren't minor discrepancies. These weren't errors in measurement that would go away with better equipment. These were fundamental failures of classical physics to explain basic phenomena. And young physicists were troubled. They could feel something was wrong. The equations that worked so beautifully for cannonballs and planets and steam engines were breaking down at atomic scales, at high frequencies, at extreme temperatures. The clockwork universe was showing cracks. But older physicists, the established authorities, mostly dismissed these problems. They were confident these anomalies would be resolved within the framework of classical physics. Some clever adjustment, some mathematical trick would make everything fit. The edifice was too beautiful, too complete, too successful to be fundamentally wrong. One physicist, though, was obsessed. His name was Max Planck, and by 1900, he was a 42-year-old professor in Berlin, conservative in temperament, deeply invested in classical physics. He'd been working on the black-body radiation problem for 6 years. 6 years of trying every classical approach he could imagine. 6 years of equations that almost worked but didn't quite. 6 years of frustration. Planck was not a revolutionary. He didn't want to overturn physics. He wanted to save it. He wanted to find the classical explanation for black-body radiation, to resolve the ultraviolet catastrophe using the familiar, comfortable laws of thermodynamics and electromagnetism. He believed in the deterministic clockwork universe. He needed it to be true. But the universe, it turned out, had other ideas. And in October of 1900, driven by desperation and intellectual honesty, Planck would make a guess, a wild, uncomfortable guess that he didn't even believe, that would crack open the clockwork universe and reveal something stranger beneath. He found an equation, a simple formula that fits the black-body radiation data perfectly across all frequencies. It worked. After 6 years of failure, he had an equation that matched the experiment exactly. He presented it to the German Physical Society on October 19, 1900, and it was recognized immediately as an accurate description of black-body radiation. But, and this is crucial, Planck had no idea why it worked. It was just an equation, a mathematical formula that fit the data. It contained a strange constant, a very small number, h equals 6.626 times 10 to the minus 34 joule seconds. Later, this would be called Planck's constant, and it would become perhaps the most important number in quantum mechanics, the fundamental unit that defines the quantum realm. But in October 1900, Planck didn't know what this constant meant. He just knew that when he put it in the equation worked. Over the next 2 months, Planck tried desperately to find a physical justification for his formula, some way to derive it from classical principles. And in this attempt, he was forced to make an assumption that violated everything classical physics stood for. He had to assume that energy wasn't continuous, that it came in discrete chunks, that atoms could only emit or absorb electromagnetic energy in integer multiples of h times the frequency. 1 chunk, 2 chunks, 3 chunks, but not 1.5 chunks. Energy was quantized. On December 14, 1900, Planck presented this derivation to the German Physical Society. This date is sometimes considered the birthday of quantum mechanics, though Planck himself didn't realize what he'd started. He thought quantization was just a mathematical trick, a convenient fiction that somehow made the equations work. He expected that eventually someone would find a way to derive the same result without this bizarre assumption. Energy was obviously continuous in the real world. It had to be. But it wasn't. And slowly, reluctantly, over the next few years, as more evidence accumulated, physicists would be forced to accept that Planck's desperate guess was actually true. Energy really was quantized. The universe really did operate in discrete chunks at the atomic scale. The smooth, continuous, deterministic clockwork was an illusion, or rather, an approximation. It worked for large-scale phenomena, but at the smallest scales, reality was grainy, discontinuous, fundamentally different from our everyday experience. The Victorian confidence was about to shatter. The certainty was about to dissolve. The clockwork universe was about to stop ticking and reveal something far stranger underneath. But in December 1900, standing at this threshold, even Planck didn't know what he'd discovered. He thought he'd found a clever mathematical solution to a technical problem. He had no idea he'd opened a door into a new world. A quantum world, where particles are waves and waves are particles, where things can be in two places at once, where the future isn't determined by the past, where observation creates reality. The revolution was beginning, and it would change everything we thought we knew about existence itself. But Max Planck, reluctant revolutionary, didn't want any of this. He just wanted to solve a puzzle about black body radiation. He wanted to make the equations work. He wanted to preserve the beautiful, deterministic, comprehensible universe that he'd spent his life studying. The universe had other plans, and those plans were far stranger, far more beautiful, and far more unsettling than anyone could have imagined. Here's what Planck proposed. Energy cannot be emitted or absorbed continuously. Instead, it comes in discrete packets. Little chunks, quanta. The size of each quantum depends on the frequency of the radiation. Mathematically, he wrote it as E equals nh nu, where E is energy, n is a whole number. 1, 2, 3, but never 1.5. H is a tiny constant that would later bear his name, and n is the frequency. Imagine you're climbing stairs instead of walking up a ramp. On a ramp, you can stop at any height. Between the first and second floor, you could stand at 1.3 floors, or 1.7 floors, or any value in between. But on stairs, you can only stand on discrete steps. You're either on the first step or the second step. You can't stand between them. Planck was saying that energy at the atomic level behaves like stairs, not ramps. For low-frequency radiation, red light, infrared, radio waves, these quantum steps are tiny, so tiny that they seem continuous, like a staircase with millions of microscopic steps that feels like a smooth ramp when you walk up it. But for high-frequency radiation, ultraviolet, X-rays, the quantum steps become large enough that atoms at ordinary temperatures simply don't have enough energy to make the jump. They can't emit these high-frequency quanta because they don't have the energy required. And this, finally, explained the ultraviolet catastrophe. The intensity of radiation doesn't increase to infinity at high frequencies because the quanta become so large that atoms rarely have enough energy to emit them. The intensity naturally drops off. The blackbody radiation curve, which had defied classical explanation for years, suddenly made perfect sense. Planck's equation matched the experimental data across all frequencies, all temperatures. It worked. But why did it work? That was the question that haunted Planck. He had an equation, yes, but no real understanding of what it meant. He'd introduced this constant h into his formula, a very small number, 6.626 times 10 to the minus 34 joule seconds. Later, this would be called Planck's constant, and it would become perhaps the most important number in all of quantum mechanics. But in December 1900, Planck didn't know what this constant represented. He just knew that when you put it in the equation worked. Think about what this constant means, though. It sets the scale of quantum effects. It's like the fundamental pixel size of reality. Below a certain scale, set by Planck's constant, the universe becomes grainy, discontinuous, quantized. Energy, which seems to flow smoothly in our everyday experience, is actually made of discrete chunks, just like matter is made of atoms. We don't notice this in daily life because these chunks are incomprehensibly small, but they're there, underlying everything. This was radical, profoundly, disturbingly radical. Energy was supposed to be continuous. You can pour any amount of water. You can apply any amount of force. Energy seemed infinitely divisible, capable of taking any value, just like classical waves. Maxwell's equations described electromagnetic waves as smooth, flowing, unbroken. A wave is a continuous thing by definition. But Planck was saying, no. At the atomic level, energy transfer happens in jumps, discrete leaps, like flipping a light switch on and off, not turning a dimmer switch smoothly. This made energy behave more like matter, which comes in atoms, indivisible units, than like waves. It suggested that the universe, at its smallest scales, wasn't smooth and continuous like we thought. It was pixelated, grainy, made of discrete units. And Planck hated this idea. He really did. He kept hoping someone would find a way to derive the same result using purely classical assumptions. He thought quantization was just a mathematical artifact, a convenient fiction that somehow made the equations work, but didn't represent physical reality. For years after his initial proposal, he tried to reconcile quantum ideas with classical physics. In his autobiography, he wrote, "My unavailing attempts to fit the elementary quantum of action somehow into classical theory continued for a number of years, and they cost me a great deal of effort. Unavailing, unsuccessful. All that effort, trying to prove his own revolutionary idea wrong, because he didn't want to be a revolutionary. He wanted to preserve the beautiful, deterministic, comprehensible universe he devoted his life to understanding. But the universe, it seemed, had other plans. The scientific community's initial reaction to Planck's proposal was skepticism mixed with confusion. Many physicists thought it was, indeed, just mathematical trickery, a clever technique that didn't reflect reality. Some simply ignored it. The equation worked, yes, but so what? Perhaps it was just an approximation, a formula that happened to fit the data without revealing any deep truth about nature. And yet, the equation kept working. Other physicists tried to find classical explanations for black-body radiation. Lord Rayleigh and James Jeans developed their own formula based purely on classical physics, the Rayleigh-Jeans law. It worked perfectly at low frequencies, but predicted infinite intensity at high frequencies, the dreaded ultraviolet catastrophe. Wilhelm Wien developed another formula that worked at high frequencies but failed at low frequencies. Only Planck's law worked across the entire spectrum. Only Planck's quantum hypothesis explained everything. Gradually, reluctantly, physicists began to take quantization seriously, not as mathematics, but as physics, as a real property of nature. And then, in 1905, a 26-year-old patent clerk named Albert Einstein took Planck's idea and ran with it in a direction even Planck hadn't imagined. If energy is emitted in quanta, Einstein reasoned, perhaps light itself consists of quanta. Not just that energy transfer happens in chunks, but that light actually is chunks. Particles of light, discrete packets of electromagnetic energy flying through space. This was an even bolder claim than Planck's. Planck had said energy is quantized at emission and absorption, the interaction between matter and radiation. But light itself, traveling through space, could still be a continuous wave. Einstein was saying no. Light itself is made of particles. Later, these would be called photons. And this explained the photoelectric effect perfectly, beautifully. When light hits metal, it sometimes knocks electrons out. But strangely, bright red light doesn't do this, no matter how intense it is, while even dim violet light does. Classical physics couldn't explain this. If light is a wave, then brighter light should mean more energy, and more energy should knock out more electrons. But that's not what happens. Einstein's explanation: each photon of light carries a discrete amount of energy determined by its frequency. E equals h times n. Planck's constant, again, showing up in a new context. A violet photon has a high frequency, therefore high energy. A red photon has a low frequency, therefore low energy. To knock an electron out of a metal requires a certain minimum energy, the work function. A violet photon has enough energy to do this. A red photon doesn't, no matter how many red photons you shine at the metal. It's like trying to break a window by throwing cotton balls at it. Doesn't matter how many cotton balls you throw, each one individually doesn't have enough energy to break the glass. This was revolutionary. For 100 years, physics had treated light as waves. Young's double-slit experiment had proven interference patterns. Maxwell's equations described electromagnetic waves propagating through space. The wave nature of light was established fact. And now Einstein was saying, light is also particles, both wave and particle. How could something be both? Einstein received the Nobel Prize in 1921 for this explanation of the photoelectric effect. Not for relativity, which is what he's famous for today, for quantum physics. For taking Planck's reluctant quantum and showing that it was real, that it was fundamental, that light itself was quantized. The irony is delicious. Einstein would later become quantum mechanics' greatest skeptic. He would spend the last decades of his life trying to prove that quantum mechanics was incomplete, that there had to be some deeper, deterministic theory underneath. God does not play dice with the universe, he famously said. But in 1905, young Einstein was quantum mechanics' boldest champion, pushing the quantum idea further than even Planck dared. Then, in 1913, a young Danish physicist named Niels Bohr applied quantum ideas to atomic structure, and suddenly the puzzle of atomic spectra made sense. Bohr proposed that electrons orbit the nucleus like planets orbit the sun, but, and here's the quantum part, they can only orbit at certain discrete distances. Quantum orbits. Each orbit corresponds to a specific energy level. Electrons can jump from one orbit to another, but they can't exist in between. When an electron jumps from a higher orbit to a lower orbit, it emits a photon whose energy equals the energy difference between the two levels. When it jumps from lower to higher, it absorbs a photon of that same energy. This explained everything about atomic spectra, why hydrogen emits light at specific wavelengths and only those wavelengths. The Balmer series, the Lyman series, the Paschen series, all those mysterious patterns that spectroscopists had cataloged for decades. Suddenly, they all made sense. Each spectral line corresponded to an electron jumping between specific quantum energy levels. The mathematics worked perfectly, and it explained why atoms are stable. Remember the classical problem. Orbiting electrons should radiate energy and spiral into the nucleus in a fraction of a second. But in Bohr's model, an electron in the lowest orbit, the ground state, can't lose energy because there's nowhere lower to fall. It's already on the bottom step. It can't fall between steps because there are no steps between. Atoms exist because of quantization. We exist because of quantization. Bohr's model was a triumph, especially for hydrogen, but it was also clearly incomplete, ad hoc, a collection of rules that worked but couldn't be deeply justified. Why only certain orbits? Bohr essentially said, because that's what fits the data. He imposed quantum conditions without really understanding where they came from. The model worked less well for more complex atoms. Something deeper was needed. The full quantum mechanics was still waiting to be discovered. But by the early 1920s, the evidence was overwhelming. Energy is quantized. That was no longer in doubt. The Compton effect, discovered in 1923, showed X-rays scattering off electrons like billiard balls, further proof that light behaves as particles. The Frank-Hertz experiment in 1914 showed electrons colliding with mercury atoms and transferring energy only in discrete amounts that match the quantum energy levels. Every new experiment confirmed it. Classical physics kept failing at atomic scales. Quantum ideas kept succeeding. Planck received the Nobel Prize in 1918 for his quantum hypothesis. By then, quantum mechanics was transforming physics. Young physicists were embracing these strange new ideas, building on them, taking them in directions Planck never imagined. But Planck himself remained uncomfortable. He never fully embraced the quantum mechanics that grew from his initial insight. He was the reluctant father of quantum theory, the man who opened a door he wished could remain closed. There's something profoundly human about this, isn't there? Planck made one of the most important discoveries in physics history, and he spent years trying to prove himself wrong. He revolutionized our understanding of reality while wishing he could preserve the old understanding. He gave us quantum mechanics while yearning for classical determinism. And yet, despite his reluctance, despite his discomfort, despite his hope that somehow it would all turn out to be a mathematical trick, the quantum was real. Energy really is quantized. Light really does consist of photons. Atoms really do have discrete energy levels. The universe really is grainy at small scales. Reality really is stranger than the smooth, continuous, deterministic clockwork we thought we lived in. But here's what I want you to consider now, and this might surprise you. Quantum mechanics isn't just something happening in laboratories with expensive equipment. It's not locked away in the microscopic realm, a strange, exotic physics that only matters for particles too small to see. Quantum effects are happening right now, all around you, in you. I know that sounds strange. When you look around your room, everything seems so classical, so normal. Chairs are chairs, walls are walls. Your coffee mug sits solidly on the table, exactly where you left it. Nothing is in two places at once. Nothing is behaving mysteriously. The world of your everyday experience seems completely disconnected from the weird quantum realm we've been discussing. But that's an illusion. Or rather, it's an approximation. The classical world you experience is built on quantum foundations. It emerges from quantum mechanics the way a photograph emerges from pixels, the way a symphony emerges from individual notes. Get close enough, look carefully enough, and the quantum nature reveals itself. Let me ask you something. Have you ever wondered how plants manage photosynthesis? I mean, really wondered about it. A plant takes sunlight, photons streaming from the sun, and converts that light energy into chemical energy with almost perfect efficiency, nearly 100% in some cases. That's remarkable. That's actually shocking when you think about it. Human-made solar panels, with all our technology, typically manage around 20% efficiency. Plants do 5 times better. How? The answer, discovered only in the last couple of decades, is quantum mechanics. Quantum coherence. Specifically, inside the photosynthetic complexes in plant cells, there are molecules called chromophores that absorb light. When a photon hits a chromophore, it creates an exciton, a quantum of excitation energy. This exciton needs to find its way to the reaction center, where the chemistry happens. But there are many possible paths through the complex molecular structure. Here's the quantum part. The exciton doesn't take one path. It takes all paths simultaneously. It exists in a quantum superposition, exploring multiple routes at once, interfering with itself like a wave, until it finds the most efficient path to the reaction center. It's doing quantum computation, essentially, to solve an optimization problem. Which path gets me to the goal fastest? The exciton explores all possibilities in parallel and collapses into the optimal solution. This was discovered through careful experiments in the 2000s, and it shocked biologists and physicists alike. Quantum coherence, which we thought was fragile, requiring near absolute zero temperatures and perfect isolation, is happening inside living cells at room temperature, in wet, noisy, biological environments. Life figured out how to use quantum mechanics billions of years ago. And it's not just plants. There's evidence that quantum effects play a role in enzyme catalysis, the chemical reactions that keep your cells running. Enzymes are absurdly good at what they do, speeding up reactions by factors of millions or billions. Classical chemistry can't fully explain this, but quantum tunneling can. Quantum tunneling, where particles pass through energy barriers they classically shouldn't be able to cross, appears to be a standard trick in enzyme toolkits. Then there's bird navigation. Many birds can sense Earth's magnetic field and use it to navigate during migration. They fly thousands of miles with astonishing precision. How do they detect magnetic fields? There are no magnetic field receptors in animal cells, no classical way to sense such weak fields. But in the 1970s, a German scientist named Klaus Schulten proposed a radical idea. Maybe birds use quantum entanglement. Here's the mechanism, as we understand it now. In bird's eyes, there are proteins called cryptochromes that contain pairs of electrons. When light hits these proteins, it can create what's called a radical pair, two electrons whose spins become quantum entangled. The Earth's magnetic field, weak as it is, affects how these entangled spins evolve. Different alignments with the magnetic field produce different chemical outcomes. The bird's visual system can detect these chemical differences, essentially seeing the magnetic field as a pattern overlaid on their vision. Quantum entanglement, Einstein's spooky action at a distance in a bird's eye, helping robins find their way south for winter. Isn't that beautiful? Isn't that just wonderfully, surprisingly beautiful? And there's your sense of smell. For decades, scientists thought smell worked through a lock and key mechanism. Molecules with certain shapes fit into receptors with complementary shapes, triggering signals to your brain. Simple mechanical interaction. But this theory had problems. Molecules with very similar shapes sometimes smell completely different. Molecules with different shapes sometimes smell similar. The lock and key model didn't quite work. In 1996, Luca Turin proposed an alternative, the vibrational theory of olfaction. Maybe your nose detects not the shape of molecules, but their vibrations, the way their atoms jiggle and oscillate. And the mechanism for detecting these vibrations? Quantum tunneling. Electrons in your olfactory receptors tunnel through molecules, and the tunneling probability depends on the vibrational frequency of the molecule. Different frequencies, different tunneling rates, different signals to your brain. Your nose might be a quantum spectroscope. This is still debated. Science is always debating, always questioning. But there's experimental evidence supporting it. And even if it turns out to be wrong, the fact that it's plausible, that quantum effects in olfaction are even being seriously considered, tells you something. Quantum mechanics isn't hiding away in the micro world. It's right there in your experience of smelling coffee, or roses, or rain on pavement. Think about that for a moment. You might be smelling quantum mechanically right now. The scent of whatever's near you, fabric softener in your sheets, the mustiness of old books, someone's perfume, might be your brain interpreting quantum tunneling events in your nose. The quantum and the everyday intertwined. And here's something even stranger. There's growing evidence that quantum effects might play a role in consciousness itself. Now, I need to be careful here. This is controversial. This is speculative. Many neuroscientists are skeptical, but it's worth mentioning because it shows how far quantum mechanics might reach into our lives. Roger Penrose, a Nobel Prize-winning physicist, and Stuart Hameroff, an anesthesiologist, have proposed that consciousness might involve quantum coherence in structures called microtubules inside neurons. These are tiny tubes made of protein that form part of the cellular skeleton. Penrose and Hameroff suggest that quantum computations happening in microtubules could be related to conscious experience, to the subjective feeling of being you. Most neuroscientists think this is unlikely. The brain seems too warm, too wet, too noisy for delicate quantum coherence. But then again, people said the same thing about photosynthesis, and look how that turned out. Maybe biology is better at preserving quantum effects than we give it credit for. Maybe the boundary between quantum and classical isn't where we think it is. I'm not saying this theory is correct. I'm saying it's remarkable that it's even possible to ask the question seriously, that we can wonder whether your thoughts, your feelings, your sense of self might have quantum origins, whether the strange, hard-to-describe quality of consciousness might reflect the strange, hard-to-describe quality of quantum mechanics. Are you still with me? I know this is a lot. We've gone from physics laboratories to plant cells to bird eyes to your nose to potentially your thoughts. That's quite a journey. But do you see the pattern? Quantum mechanics isn't confined to one realm. It's not just about particles in accelerators or electrons in atoms. It's woven throughout reality, including biological reality, including you. So, why don't we notice? If quantum effects are everywhere, if they're in plants and birds and our own cells, why does the world seem so classical? Why don't we see quantum superpositions of cats and popo and tables and coffee mugs? Why does everything seem solid, definite, located in one place at one time? That's the question that leads us deeper. And the answer, the beautiful, subtle answer that took physicists decades to work out, has to do with something called decoherence. The universe has a mechanism, a gentle, continuous process that erases quantum effects at large scales. Not because quantum mechanics stops being true, but because the environment constantly interacts with objects, measuring them in countless tiny ways, forcing them to behave classically. But I'm getting ahead of myself. Before we talk about decoherence, before we explain why the classical world emerges from quantum foundations, let's just sit with this realization for a moment. Quantum mechanics is everywhere. In every leaf, every bird, every breath you take. The universe is quantum to its core. The strange, probabilistic, wave-like nature of reality doesn't go away at large scales. It just becomes hidden, averaged out, smoothed over by the sheer number of particles and interactions involved. You are a quantum system. Your body contains something like 10 to the 28th atoms, and every single one of them is behaving quantum mechanically. Your electrons are in superpositions. Your molecules are tunneling. Your cells might be using entanglement. The fact that you feel classical, that you experience yourself as a definite, localized person with specific thoughts and feelings, is itself something that needs explaining. The question isn't, where does quantum mechanics apply? The question is, why doesn't everything look quantum all the time? This might be the most important question in all of quantum mechanics. If quantum effects are everywhere, why don't you ever feel like you're in two places at once? Why does the chair across the room look like it's definitely over there, not here and there simultaneously? Why does the classical world feel so solid, so definite, so utterly unquantum? For decades, this was physics' deepest puzzle, and the answer, when it finally came, was both subtle and profound. It's not that quantum mechanics stops being true at large scales. It's not that there's some magical size threshold where quantum effects switch off. It's that the environment, everything around you, is constantly measuring quantum systems, collapsing their superpositions so rapidly and so completely that the quantum nature becomes invisible. This process is called decoherence, and I want you to understand it, really understand it, because it's one of the most beautiful ideas in all of physics. It explains why the world looks classical, even though it's fundamentally quantum. It shows how the universe, in a sense, observes itself. Let me start with something simple. Imagine a single atom, completely isolated from everything else in the universe, suspended in a perfect vacuum, shielded from all light, all radiation, all matter. This atom can exist in a quantum superposition. It can be in multiple energy states at once, or multiple positions at once, genuinely in multiple states simultaneously until something measures it. But here's the thing. Nothing in the universe is actually isolated like this. Everything is surrounded by environment, air molecules bouncing off it, photons from ambient light scattering off it, cosmic rays passing through it, thermal radiation from nearby objects interacting with it. Even in the emptiest regions of space, there's the cosmic microwave background, remnant radiation from the Big Bang, permeating everything. Each of these interactions, each photon scattering, each molecule colliding, acts as a tiny measurement, a tiny observation. And each measurement, no matter how small, carries information about the system into the environment. This photon bounced off the atom at this angle, carrying information about where the atom was. That air molecule transferred this much momentum, revealing information about the atom's motion. The information spreads. The photon travels away. The air molecule bounces into other molecules. The information about the quantum system gets distributed into the environment, becoming more and more scrambled, more and more difficult to recover. And as this happens, the quantum superposition collapses. Not because of any mysterious process, not because consciousness observes it, but simply because the environment has measured it. Think about it this way. Imagine you're trying to keep a secret. As long as nobody knows, the secret remains yours. But if you tell one person, and they tell someone else, and that information spreads through a network of people, the secret becomes public knowledge. You can't take it back. The information has delocalized. It's everywhere and nowhere, mixed into the collective knowledge of many minds. Decoherence is like that. The quantum information about a superposition gets leaked into the environment, becoming so thoroughly mixed and scrambled that it's essentially lost forever. And once that information is lost, the superposition is gone. The system behaves classically. Here's what's remarkable. This happens incredibly fast for large objects. For something the size of a dust particle, decoherence happens in about 10 to the minus 31 seconds. That's a decimal point followed by 31 zeros and then a 1. Practically instantaneous. For something the size of you, decoherence would be even faster, incomprehensibly fast. You're interacting with so many air molecules, so many photons, radiating so much heat that any quantum superposition would collapse essentially immediately. This is why you never feel like you're in a superposition, not because you're not quantum mechanical, you are, but because your environment is measuring you constantly, relentlessly, forcing you to be in a definite state. The same goes for chairs and tables and coffee mugs, and everything else in your everyday experience. They're all being observed by their environment all the time, and this observation creates the classical world. But, and this is crucial, decoherence isn't fundamental to quantum mechanics. It's not a new law of physics. It emerges naturally from the standard rules of quantum mechanics when you account for environmental interactions. The equations are the same equations that describe isolated quantum systems. Nothing new is added. Decoherence is just what happens when quantum systems interact with complex environments. Let me give you a specific example, something physicists have studied carefully. Imagine a photon, a particle of light, traveling through space. While it's traveling, before it interacts with anything, it can be in a superposition of different polarizations. Horizontal and vertical polarization at the same time, genuinely both until measured. Now, imagine this photon passes through the air. Air molecules scatter some of the photon's energy. Each scattering event depends on the polarization. Horizontal polarization scatters slightly differently from vertical polarization. The air molecules, after scattering, contain information about which polarization the photon had. That information spreads as the air molecules collide with other molecules. Within nanoseconds, the information about the photon's polarization has been distributed into trillions of air molecules. The photon's superposition of polarizations has been destroyed, not by some mysterious collapse, but by information leakage into the environment. The photon now behaves as if it has definite polarization. The quantum coherence is gone. This is decoherence in action. And here's something that might comfort you or might unsettle you, depending on your perspective. This means observation doesn't require consciousness. For most of the 20th century, there was this idea floating around, popularized by some interpretations of quantum mechanics, that consciousness was special, that conscious observation collapsed wave functions in a way that unconscious measurements didn't. Some people found this exciting, this suggestion that mind played a fundamental role in reality. But decoherence shows it's not necessary to invoke consciousness. An air molecule observes just as well as a human does. A photon measures just as effectively as a detector. Observation, in quantum mechanics, just means interaction. The transfer of information from the system to the environment. Nothing mystical, nothing requiring awareness. Does this disappoint you? I hope not. I think there's something beautiful about it. The universe doesn't need us to observe it into existence. It observes itself. Every particle interacting with every other particle, constantly creating a web of measurements that gives rise to classical reality. We're part of that web, certainly. When you look at something, you're observing it. Photons from your eye's light sources bouncing off objects and returning to your retina. But you're not special in this regard. The wall behind you is observing you just as much through thermal radiation and air molecule interactions. Reality emerges from this constant mutual observation. Everything measuring everything else. Information spreading through the environment like ripples on a pond, creating the stable, definite, classical world we experience. But here's where it gets even more interesting. Decoherence explains why we don't see quantum superpositions of large objects, but it doesn't explain where the definiteness comes from. When a quantum system decoheres, it behaves as if it's in one definite state. But the equations of quantum mechanics still technically describe it as being in a superposition, just one that's entangled with the environment in such a complex way that it's impossible to detect the superposition. This is subtle. Let me try to explain it. Before decoherence, you might have an atom that's genuinely in a superposition. 50% state A, 50% state B. After decoherence, the atom plus environment is in a state like if atom is in A, environment recorded A, and if atom is in B, environment recorded B. The atom looks like it's in a definite state when you examine just the atom, but the full quantum description still contains both possibilities, just correlated with different environment states. So what happened to the other possibilities? Where did they go? This is where interpretations of quantum mechanics diverge. Some say the other possibilities are real, but inaccessible, branching off into parallel worlds. Some say there's an objective collapse that genuinely eliminates the other possibilities. Some say the question itself is meaningless because we can only ever observe one outcome. But regardless of interpretation, decoherence explains the practical question. Why does the world look classical? And the answer is this beautiful, almost poetic idea. The environment is constantly, gently, invisibly erasing quantum coherence, selecting out particular states, creating the illusion or the reality, depending on your interpretation, of definite outcomes. Think about waves on the ocean. Far from shore, waves can be complex, with different ripples interfering with each other, creating intricate patterns. But as waves approach the beach, they interact with the sandy bottom, with rocks, with the shore itself. The complexity gets smoothed out. By the time the wave reaches your feet, it's a simple, definite thing. A wave coming in, breaking, receding. Decoherence is like that. Quantum systems start out potentially complex, in superpositions with intricate interference patterns. But as they interact with the environment, the complexity gets smoothed out, averaged over, until what remains is simple, classical, definite. The quantum interference is still there in principle, buried in the correlations with the environment, but it's impossible to access. For all practical purposes, it's gone, and this happens continuously. Right now, as you listen to this, air molecules are bouncing off you, photons are scattering from you, heat is radiating from you, and all of this is constantly decohering any quantum superpositions that might try to form. The environment is measuring you, observing you into definite existence, trillions upon trillions of times per second. You are being observed by the universe itself, not watched by some cosmic consciousness, but measured by the countless interactions between your atoms and the rest of reality. And this observation, this decoherence, is what makes you feel real, solid, located in space and time. Isn't that strange? Isn't that wonderful? The reason you experience a classical world isn't because quantum mechanics is wrong or limited. It's because you're embedded in an environment that won't stop measuring you. The universe is too connected, too interactive, for quantum superpositions to survive at large scales. Decoherence is the price of being part of the world, the inevitable consequence of not being perfectly isolated. But here's a thought that might send a shiver down your spine, or might fill you with quiet awe. In principle, if you could perfectly isolate an object from all environmental interactions, perfect vacuum, perfect shielding, absolute zero temperature, even a large object could maintain a quantum superposition. It would behave quantum mechanically. You could, in theory, put a virus, or maybe even a small bacterium, in a superposition of being in two places at once. Physicists are working on this, pushing the boundaries of what can be kept quantum. They've achieved quantum superpositions of increasingly large molecules. They're dreaming of quantum superpositions of tiny mirrors, microscopic cantilevers, perhaps someday something visible to the naked eye. Not because it's useful, though quantum technologies might benefit, but because we want to know, where is the boundary? How large can quantum superpositions get? Maybe there is no boundary. Maybe it's just a question of how well you can isolate things. Maybe, in some distant future, in a laboratory with technology beyond our current dreams, someone will put a grain of sand in superposition, or a virus, or who knows what. And at that moment, the classical world will reveal itself completely as an emergent phenomenon, not a fundamental truth. But in your everyday life, in this room, at this moment, decoherence reigns. The environment is watching. The quantum world is hidden beneath a veil of interaction. And what you experience is the classical surface, the definite, solid, sensible reality that emerges from quantum foundations. And there's something comforting about that, I think. The world appears stable not because it is fundamentally stable, but because the universe is so thoroughly interconnected that stability emerges. You exist as a definite person, with definite thoughts and definite experiences, because the environment won't let you be otherwise. Decoherence is the universe's gentle eraser, constantly smoothing out quantum strangeness, creating the classical world we know. And now that you understand it, you can appreciate the paradox. Quantum mechanics is everywhere, but decoherence makes it invisible. The quantum and the classical aren't separate realms. They're two aspects of the same reality, with decoherence being the bridge between them. Now, I want to show you something so counterintuitive that when physicists first predicted it, even they had trouble believing it. Something that suggests observation doesn't just reveal reality, it can actually prevent change from happening. It's called the quantum Zeno effect. And yes, it's named after Zeno of Elea, the ancient Greek philosopher who gave us those famous paradoxes. You might remember them from school. Achilles and the tortoise. The arrow that can never reach its target because it must first travel half the distance, then half of what remains, then half of that, infinitely subdividing space until motion becomes impossible. Zeno's paradoxes were meant to show that motion is an illusion, that change is impossible. They're paradoxes because obviously things do move. We see it all the time. Yet the logic seems airtight. The resolution, as you probably know, involves calculus, an infinite series. An infinite number of steps can add up to a finite distance if each step gets small enough fast enough. Motion is possible. Zeno was wrong. But in quantum mechanics, Zeno was right. Sort of. Not about motion in the classical world, but about quantum transitions. In the quantum realm, if you observe a system continuously, you really can prevent it from changing. Watch something closely enough, and you freeze it in place. Not metaphorically. Actually. Let me explain how this works, because it's genuinely strange. Imagine you have an unstable atom, something radioactive that will eventually decay. Maybe it has a half-life of 1 second, meaning there's a 50% chance it decays in the first second. Normally, you just wait and see when it decays. The atom sits there, existing in a quantum superposition of decayed and not decayed states, gradually evolving according to Schrödinger's equation, until eventually something measures it and you find out whether it decayed or not. But what if instead of waiting, you measure whether the atom has decayed? Not once, but repeatedly. Every millisecond, say. Check. Has it decayed? No, still there. Check again. Has it decayed? No, still there. Check again, and again, and again. Here's what happens. The atom doesn't decay, or rather, it decays much, much more slowly than it should. The continuous measurements reset the quantum evolution, preventing the atom from transitioning into the decayed state. The more frequently you measure, the more you suppress the decay. In the limit of truly continuous measurement, the atom never decays at all. You've frozen it in its initial state through the act of observation. This isn't speculation or philosophical musing. This is experimentally verified quantum mechanics. The quantum Zeno effect has been observed in laboratories, with atoms, with ions, with various quantum systems. It's real. Observation can prevent change. Why does this happen? The mathematics is complex, but the intuition goes something like this. When you measure a quantum system, you collapse its wave function. You force it into a definite state. In this case, the not decayed state, since that's what your measurement found. The wave function immediately starts evolving again, beginning to spread out, exploring the possibility of decay. But if you measure again very quickly, before it's had much time to evolve, you'll almost certainly find it still in the not decayed state, and your measurement collapses the wave function back to that state again. The evolution keeps getting reset before it can make significant progress. Think of it like trying to watch a pot of water boil. Except in this case, if you watch closely enough, constantly checking the temperature, the water genuinely doesn't boil. Not because watching prevents heat transfer, that's just a classical saying, but because in the quantum realm, observation has real physical effects. Or imagine you're trying to fall asleep, and someone keeps asking, "Are you asleep yet? Are you asleep yet?" Each time they ask, they wake you up, resetting your transition towards sleep. You never manage to fall asleep because the checking process keeps interrupting the transition. The quantum Zeno effect is like that, except it's not annoying, it's fundamental physics. Now, you might be wondering, doesn't this violate energy conservation or time evolution or something fundamental? How can you just prevent an atom from decaying? The atom still has the same energy, the same internal state. Shouldn't it decay regardless of whether you're watching? The answer is subtle. You're not preventing the decay by changing the atom's properties. You're preventing it by constantly collapsing the wave function before the decay probability becomes significant. The atom is still trying to decay. The quantum amplitude for the decayed state is still growing, but you keep resetting that amplitude through measurement. It's like running a race where someone keeps teleporting you back to the starting line every few meters. You're still trying to run, but you never make progress. And here's something even stranger. There's also an anti-Zeno effect. Under certain conditions, frequent measurements can actually accelerate transitions instead of preventing them. This happens when the measurement interval matches certain resonances in the quantum system. It's like pushing someone on a swing. Push at the right frequency, and you amplify the motion. The quantum system, measured at just the right rate, can be driven more quickly toward the decayed state. So, observation can freeze quantum systems or speed up their evolution, depending on the details. Measurement isn't just passive recording. It's an active participant in quantum dynamics. Do you find this unsettling? I do, sometimes. There's something almost eerie about it. The idea that reality is shy, that quantum processes hesitate when observed, that watching can prevent change. It feels like the universe is playing tricks on us, behaving differently when we're paying attention versus when we're not. But remember what we learned about decoherence. Observation isn't mystical. It's just interaction. The quantum Zeno effect happens not because the universe is aware of being watched, but because measurement physically interacts with the system, collapsing the wave function, resetting the quantum evolution. It's a consequence of how quantum mechanics works, not some spooky consciousness-related phenomenon. Still, it raises fascinating questions. Could you use the quantum Zeno effect to preserve quantum information? To protect quantum bits in a quantum computer from decaying? Actually, yes. Researchers are exploring exactly this. By frequently measuring certain properties of quantum systems, you can suppress unwanted transitions, keeping your quantum information stable longer. The very act that causes decoherence, measurement, can also be used strategically to prevent other forms of decoherence. It's deliciously paradoxical. Or here's a wild thought. Could the quantum Zeno effect have implications for time itself? If observation can freeze quantum transitions, does that mean time flow is somehow related to observation? Is time itself emergent from quantum evolution, and does it slow down when evolution is suppressed? These are questions physicists argue about over coffee and whiteboards. There are no definitive answers yet, but the quantum Zeno effect opens up these strange possibilities, these weird connections between observation, change, and time that wouldn't make sense in classical physics. Let me give you a specific experimental example, something real that physicists have done. In 1990, a team led by Wayne Itano at the National Institute of Standards and Technology took a collection of beryllium ions, about 5,000 of them, and put them in a carefully controlled electromagnetic trap. They used lasers to prepare the ions in a specific quantum state, then applied an oscillating magnetic field designed to drive transitions to a different state. Under normal circumstances, the ions would oscillate between the two states at a predictable rate. But then they added measurements, frequent pulses of light, to check which state the ions were in, and they found that with frequent measurements, the transition rate dropped dramatically. The ions stayed in their initial state much longer than they should. The more frequent the measurements, the stronger the suppression. They'd experimentally demonstrated the quantum Zeno effect. Since then, dozens of similar experiments have been done with various quantum systems. The effect is robust, reproducible, well understood theoretically. It's not controversial among physicists. It's just one of those strange facts about quantum mechanics that still manages to surprise us when we think about it carefully. And it connects to something deeper, something we touched on earlier when discussing decoherence. The environment is constantly measuring quantum systems, constantly collapsing wave functions. But in most cases, the environment doesn't measure the same property repeatedly. It's more like random measurements of various properties, which causes decoherence and creates classical behavior. But if the environment were to repeatedly measure the same property over and over with the right timing, it could suppress transitions through the quantum Zeno effect. Does this happen in nature? Maybe. There might be situations where environmental measurements are coherent enough, repetitive enough, to cause Zeno-like effects. In fact, some researchers have suggested that the quantum Zeno effect might play a role in protecting quantum coherence in biological systems, like the photosynthesis we discussed earlier. Maybe life has evolved ways to structure environmental interactions so that certain quantum states are stabilized through Zeno-like mechanisms. That's speculative, of course, but it shows how these quantum effects we're exploring aren't just laboratory curiosities. They might be operating in the real world, in living systems, in ways we're only beginning to understand. Here's what I want you to take away from this. Quantum mechanics has a very strange relationship with observation. Observation isn't just passive. It doesn't just reveal pre-existing properties. It actively shapes quantum evolution. Frequent observation can freeze quantum systems in place. Infrequent observation allows them to evolve freely. The rate and timing of measurement affect how quantum systems behave. This is fundamentally different from classical physics, where observation is passive. If you watch a ball rolling down a hill, your watching doesn't affect the rolling, not in any meaningful way. The ball rolls the same whether you're watching or not, whether you check its position once or 1,000 times. But in quantum mechanics, how and when you observe matters profoundly. And this raises a question we'll explore more as we continue. What exactly is measurement? What counts as observation? We said earlier that any interaction constitutes measurement, that consciousness isn't required. But are all interactions equally effective at collapsing wave functions? Are some interactions more measurement-like than others? What makes something a measurement versus just a weak interaction? These questions lead to deep waters, to interpretations of quantum mechanics, to debates that have raged for a century. But they're worth asking, worth contemplating, because they go to the heart of what reality is and how it comes into being. For now, though, just rest with the strangeness of the quantum Zeno effect. Rest with the idea that the universe is shy, that quantum processes can be frozen by observation, that watching does something in the quantum world. It's one more piece of evidence that reality is far stranger than our everyday experience suggests, that beneath the familiar surface lies something deeply, beautifully weird. And we're going to keep exploring that weirdness together, going deeper and deeper into quantum strangeness, discovering how particles can tunnel through barriers, how empty space isn't empty, how the future might affect the past. The quantum world has so many surprises waiting for us. But perhaps you're ready for one of the most counterintuitive quantum phenomena of all, quantum tunneling, where particles pass through walls they shouldn't be able to pass through, where the impossible becomes routine, where the universe reveals itself as fundamentally probabilistic rather than deterministic. That's where we're heading next. Quantum tunneling might be the most important quantum effect you've never really thought about. Because without quantum tunneling, the sun wouldn't shine, your body wouldn't generate heat, stars wouldn't form, life wouldn't exist. And yet, it's happening all around you, constantly, invisibly. making the universe possible. Let me start with the classical impossibility, so you can appreciate just how strange the quantum reality is. Imagine you're rolling a ball toward a hill. If the ball doesn't have enough energy to reach the top of the hill, it rolls partway up, stops, and rolls back down. It doesn't matter how many times you try. If the ball lacks the energy to crest the hill, it's not getting to the other side. This is classical physics. Energy is conserved. You can't cross barriers you don't have the energy to overcome. Simple. Obvious. Wrong. In quantum mechanics, particles can pass through barriers even when they don't have enough energy. Not by going over the barrier. They're not somehow borrowing energy or finding a hidden path. They simply appear on the other side, having passed through a region they classically couldn't enter. It's as if you rolled a ball at a hill, watched it roll partway up and stop, and then suddenly found it on the other side, having passed through the hill itself. Now, the usual explanation involves particles tunneling through the barrier, and that's the language physicists use. But I want to give you a deeper picture, one that's closer to what's actually happening according to quantum mechanics. Because particles aren't really tunneling through anything. They're not little bullets boring through walls. Remember, in quantum mechanics, particles aren't located in one definite place until they're measured. They're described by wave functions, probability waves that extend through space. A particle is, in a real sense, spread out, existing as a field of possibilities rather than a point-like object. When a quantum particle encounters a barrier, its wave function doesn't stop at the barrier's edge. It extends into the barrier, diminishing exponentially, but never quite reaching zero. There's a small but non-zero amplitude for the particle to exist inside the barrier and on the far side. The particle isn't in one place, trying to get through. It's already on both sides, simultaneously, as a wave of probability. When you measure where the particle is, you might find it on the near side of the barrier. That's most likely. But you might also find it on the far side. And if you do, we say the particle has tunneled through. But really, it was already there, as a possibility, as part of its wave function. Measurement just selected which possibility became reality. Does that make sense? I know it's subtle. The particle isn't traveling through the barrier. It's not taking time to tunnel. It's simply that its quantum wave function extends beyond the barrier, and there's a probability, usually small but non-zero, of finding the particle there when you measure it. Let me give you some numbers to make this concrete. The probability of tunneling depends on the barrier's height and width and on the particle's energy. For a barrier much higher and wider than the particle's energy, the tunneling probability might be 10 to the minus 20 or 10 to the minus 30, incredibly tiny. For a billion particles approaching such a barrier, maybe one tunnels through, but one is enough. Because quantum mechanics deals in probabilities, rare events become inevitable given enough attempts. And nature attempts constantly. Every moment, countless particles encounter barriers, and some fraction, however small, tunnel through. Over cosmic timescales, across astronomical numbers of particles, tunneling isn't just possible, it's inevitable. Here's where it gets beautiful. The sun shines because of quantum tunneling. Let me explain this because it's genuinely wonderful. The sun is powered by nuclear fusion, hydrogen nuclei smashing together to form helium, releasing tremendous energy. But hydrogen nuclei, protons, are both positively charged. Like charges repel, two protons approaching each other feel an enormous electrostatic repulsion, an energy barrier that pushes them apart. For fusion to occur, protons need to get close enough for the strong nuclear force to bind them together. But the strong force only operates at extremely short distances, about 10 to the minus 15 meters. To reach that distance, protons need to overcome the electrostatic repulsion barrier. Classically, this requires temperatures of billions of degrees. The sun's core is only about 15 million degrees, incredibly hot, but nowhere near hot enough for classical fusion. The protons in the sun's core don't have enough energy to overcome the repulsion barrier. And yet, fusion happens. Billions upon billions of fusion reactions every second, powering the sun, warming the earth, making life possible. How? Quantum tunneling. The proton's wave functions extend through the repulsion barrier. Most of the time, when protons collide, they bounce off each other. The measurement of their position finds them on opposite sides of the barrier. But occasionally, rarely, but often enough given the sun's vast number of particles, the measurement finds them close enough together for the strong force to bind them. They've tunneled through the electrostatic barrier. The sun shines because of quantum impossibility becoming quantum reality. Every photon that warms your face, every ray of sunlight filtering through your window, every green leaf powered by photosynthesis, all of it traces back to quantum tunneling in the sun's core. Stars exist because particles can be on both sides of barriers simultaneously. And it's not just the sun. Every star in the universe, and there are about 10 to the 24 of them, that's a trillion, burns through quantum tunneling. Without this effect, stars would never have formed. The universe would be a cold, dark place of hydrogen gas that could never ignite. There would be no heavy elements, no planets, no complexity, no life, no you. Quantum tunneling made the universe interesting. But it's not just cosmic. Tunneling happens in your body right now. Your cells generate heat through chemical reactions, metabolism, the breakdown of nutrients into energy. Many of these reactions involve hydrogen atoms hopping between molecules. Classically, some of these hops require more energy than the molecules typically have at body temperature. But quantum tunneling allows hydrogen atoms to tunnel through energy barriers, enabling reactions that would be impossibly slow classically. In fact, there's evidence that enzymes, those remarkable biological catalysts we mentioned earlier, often work by positioning molecules so that quantum tunneling becomes more probable. The enzyme creates a geometry where the tunneling distance is minimized, dramatically increasing the tunneling rate. Your cells might be quantum engineers, arranging molecules to exploit tunneling for biochemical reactions. Here's another place you've definitely encountered tunneling, even if you didn't know it: electronics. Every electronic device you use, computers, phones, even simple circuits, relies on semiconductors. And semiconductors only work because of quantum tunneling. When you make transistors smaller and smaller, as we've been doing for decades following Moore's law, eventually they become so small that electrons can tunnel through the insulating barriers that are supposed to contain them. This leakage current from tunneling is actually a major challenge in modern chip design. But tunneling also enables technology. Flash memory, the storage in your phone, your computer, your USB drives, works by trapping electrons in tiny wells using quantum barriers. To write data, you apply a voltage that allows electrons to tunnel through the barrier into the storage wells. To erase, you allow them to tunnel back out. Your devices store information by manipulating quantum tunneling. And there's an entire imaging technology based on tunneling, scanning tunneling microscopy, or STM. This technique, developed in the 1980s and awarded the Nobel Prize in 1986, allows us to see individual atoms. Here's how it works. You bring an incredibly sharp needle, just one atom at the tip, very close to a surface, so close that electrons can tunnel between the tip and the surface. The tunneling current is extraordinarily sensitive to distance. Moving the tip, even a tenth of a nanometer, changes the current dramatically. By scanning the tip across the surface and measuring the tunneling current, you can map out the atomic landscape. The images are stunning. You can see atoms arranged in patterns. You can watch individual molecules. You can even manipulate single atoms, pushing them around like tiny marbles. All because quantum tunneling allows electrons to cross the gap between the tip and surface, and the tunneling probability tells you how far apart they are. Think about that for a moment. We can see atoms, not with light, because atoms are smaller than light wavelengths. But with quantum tunneling, we're using one weird quantum effect to observe the quantum nature of matter itself. It's almost poetic. Now, you might be wondering, if particles can tunnel through barriers, why don't you tunnel through your chair when you sit down? Why don't objects spontaneously tunnel through walls? The answer is the same as why you don't see quantum superpositions of cats: decoherence and probability. For something as large as you, or even as large as a dust particle, to tunnel through a barrier, every single atom in your body would need to tunnel simultaneously. The probability of this happening is incomprehensibly small, not zero. Technically, quantum mechanics never gives exactly zero probability, but so close to zero that it would never happen in the entire age of the universe, even if you tried constantly. Tunneling probabilities decrease exponentially with the barrier width and with the mass of the particle. Electrons, being incredibly light, tunnel relatively easily. Protons, being about 2,000 times heavier, tunnel much less readily. Entire atoms tunnel even less. Molecules, less still. Something made of 10 to the 28 atoms like you? The probability is so vanishingly small, it might as well be zero. But for individual particles, for single electrons or protons, or atoms, tunneling is commonplace. And when you have enormous numbers of particles attempting to tunnel, like in the sun or in chemical reactions, the rare becomes routine. There's something almost philosophical about quantum tunneling, don't you think? It suggests that barriers aren't absolute, that impossibilities are just improbabilities, that given enough time, enough attempts, the unlikely becomes inevitable. In a sense, quantum mechanics is optimistic. Nothing is truly forbidden. Everything has some probability, however small. Classical physics was deterministic, but rigid. Things either had enough energy to overcome barriers or they didn't. The universe ran on strict rules with no exceptions. Quantum mechanics is probabilistic, but flexible. Things can happen that classically shouldn't. The universe is full of small miracles, tiny violations of classical expectations, happening constantly at the atomic scale. And these small miracles add up to everything. The sun shining, chemistry working, life existing. You being here, listening to this, contemplating the nature of reality. All of it made possible, at least in part, by particles being in multiple places simultaneously, by wave functions extending through barriers, by the quantum impossibility of definite location. Tunneling reminds us that particles aren't little balls bouncing around. They're waves of probability, fields of potential existence, smeared across space until measurement collapses them into definite locations. And before that collapse, they're everywhere. Their wave function is non-zero, which includes, in principle, on both sides of any barrier. The universe is less solid than it appears, more fuzzy, more probabilistic, more interconnected. Particles aren't separate from their surroundings in the way classical objects are. They're embedded in space, extending through it, overlapping with it. Barriers don't divide space into absolute regions of accessible and inaccessible. They just modify probabilities, making some outcomes more likely than others. And isn't there something freeing about that? The universe isn't a prison of classical constraints. It's a space of quantum possibilities, where the unlikely can happen, where barriers are permeable, where particles explore multiple realities simultaneously until measurement selects one. We're going to encounter more strangeness as we continue. We're going to discover that even empty space isn't truly empty, that the vacuum itself seethes with quantum activity, particles and antiparticles popping in and out of existence, making the void less void-like than we ever imagined. But that's ahead of us. For now, just rest with quantum tunneling, with the knowledge that particles are everywhere and nowhere, that barriers are probabilistic rather than absolute, that the sun shines because of quantum impossibility, that your existence depends on particles being able to be in places they classically couldn't reach. Tunneling is happening right now, all around you, inside you, enabling the chemistry of life, the warmth of your body, the electronic devices near you. The quantum world isn't somewhere else. It's here, underlying everything, making reality possible through subtle violations of classical expectations. And we're only beginning to understand just how deeply quantum mechanics shapes the world we experience. Now, I want to ask you to contemplate something a little stranger. What about empty space itself? What about the vacuum, the void, the nothing between things? You might think that empty space is, well, empty. That if you removed all the particles, all the energy, everything, if you created a perfect vacuum, you'd have nothing. True nothingness. The absence of everything. A blank canvas. Zero. But quantum mechanics says no. Even empty space isn't empty. The vacuum, it turns out, is one of the most interesting places in quantum physics. It's not nothing. It's a seething ocean of quantum activity, constantly churning with particles that pop into existence and vanish again, fields that fluctuate wildly at tiny scales, energy that appears from nowhere and disappears just as quickly. This isn't poetry or metaphor. This is experimentally verified, mathematically rigorous quantum mechanics. The vacuum is alive with quantum fluctuations, and understanding this, really understanding what it means, changes how you think about reality itself. Let me start with something fundamental: the Heisenberg uncertainty principle. You've probably heard of it. It says you can't know both the position and momentum of a particle with perfect precision simultaneously. The more precisely you measure one, the less precisely you can know the other. This isn't about measurement limitations or technology. It's fundamental to quantum mechanics. Position and momentum don't have definite values simultaneously. They're complementary properties linked by uncertainty. But there's another form of the uncertainty principle, one that's less famous but equally important: the energy-time uncertainty principle. It says that the uncertainty in energy multiplied by the uncertainty in time must be greater than or equal to Planck's constant divided by 4p. Mathematically, delta E times delta T is greater than or equal to h bar over 2, where h bar is h divided by 2p. What does this mean? It means that if you look at a very short time interval, a brief moment, the energy in that moment is fundamentally uncertain. It can fluctuate wildly. Energy can appear and disappear as long as it does so quickly enough that the uncertainty principle is satisfied. Think about it this way: if you glance at your bank account for just a split second, there's uncertainty in the balance during that instant. In that brief moment, money could appear and disappear, and as long as it balances out fast enough, the universe allows it. That's obviously not how bank accounts work, but it's genuinely how energy works in quantum mechanics. This means that even in empty space, even in a perfect vacuum with no particles, no fields, nothing, the energy is fluctuating. Virtual particles can pop into existence, exist briefly, and then annihilate back into nothingness. An electron and a positron, particle and antiparticle, can spontaneously appear, exist for a tiny fraction of a second, and then collide and vanish. All permitted by the energy-time uncertainty principle, as long as they don't stick around too long. These are called virtual particles. And before you ask, yes, they're real. Virtual doesn't mean imaginary or fictitious. It means they exist temporarily, borrowing energy from the vacuum's quantum fluctuations. They have measurable effects. They influence real particles. They're part of the quantum vacuum structure. The vacuum, then, isn't empty. It's a quantum foam, constantly frothing with particle-antiparticle pairs appearing and disappearing, fields fluctuating wildly at tiny scales. If you could somehow magnify empty space, zooming down to the Planck scale, about 10 to the minus 35 meters, you'd see this churning chaos, this sea of quantum activity. We can't directly observe individual virtual particles. They exist too briefly, and measuring them would give them real energy, making them real particles. But we can observe their collective effects. And one of the most beautiful demonstrations of this is the Casimir effect, discovered theoretically in 1948 by Dutch physicist Hendrik Casimir and measured experimentally in various forms over subsequent decades. Here's the setup. Take two perfectly flat, perfectly parallel metal plates and place them very close together in a vacuum, just a few micrometers apart. Now, classical physics says nothing should happen. There's a vacuum between the plates. No particles, no forces. The plates should just sit there, but they don't. They're pushed together by a tiny force. Not pushed by anything physical, pushed by the vacuum itself. Pushed by the absence of certain virtual particles between the plates. Let me explain. In the vacuum outside the plates, all wavelengths of virtual photons can exist. Short wavelengths, long wavelengths, everything. But between the plates, only wavelengths that fit exactly between the plates, wavelengths that are integer divisions of the gap, can exist. Long wavelengths are excluded. This means there are more virtual particle fluctuations outside the plates than between them. This imbalance creates pressure. The plates are pushed together by the difference in quantum vacuum energy. It's a tiny force, on the order of 10 to the minus 7 newtons for square centimeter plates a micrometer apart. But it's measurable, and it's been measured many times, with results matching theoretical predictions beautifully. Two metal plates in a vacuum are pushed together by nothing. Or rather, by the quantum something that fills the nothing. Doesn't that just delight you? The universe has pressure from nothingness. Empty space pushes things together because there are fewer quantum fluctuations in small gaps than in open space. The Casimir effect is one of the most direct demonstrations that the vacuum isn't empty, that quantum fields are real, that fluctuations matter. And these fluctuations have other observable effects. There's something called the Lamb shift, discovered in 1947 by Willis Lamb, which is a tiny shift in the energy levels of hydrogen atoms caused by the interaction between the electron and virtual photons in the vacuum. Classical quantum mechanics, without accounting for vacuum fluctuations, predicts that certain energy levels should be exactly the same. But they're not. They're shifted slightly. Why? Because the electron is constantly interacting with virtual photons that pop in and out of existence. These interactions subtly change the electron's energy. Lamb won the Nobel Prize for measuring this shift. It was crucial evidence that quantum field theory, which treats the vacuum as full of fluctuating fields, was correct. The vacuum is active, interactive, influential. It's not a stage on which particles perform. It's part of the performance. There's also something called the anomalous magnetic moment of the electron. Classical quantum mechanics predicts a specific magnetic moment for the electron. But when you account for the electron interacting with virtual particles, emitting and reabsorbing virtual photons, briefly splitting into virtual electron-positron pairs, the magnetic moment changes slightly. The theory and experiment agree to more than 10 decimal places. It's one of the most precisely verified predictions in all of physics. And it only works if you include the vacuum fluctuations. So the vacuum is constantly active, full of virtual particles, influencing real particles, creating measurable forces. But here's where it gets philosophically interesting. What does this mean for the concept of nothingness? What does it mean for empty space? In classical physics, empty space was truly empty. A vacuum was the absence of everything. You could, in principle, remove all matter, all energy, and be left with pure nothingness. But quantum mechanics says no. You can't remove the quantum fields. They're fundamental to space itself. Even at the minimum energy state, the vacuum state, the fields are still there, still fluctuating. The 0-point energy, the irreducible minimum energy of quantum fields, is never truly zero. This suggests that space itself is a thing, not nothing. It has structure, properties, energy. The vacuum is a medium, a quantum field condensate, a something rather than a nothing. You can't have space without quantum fields, and you can't have quantum fields without fluctuations. Some physicists even think the vacuum might have layers, different phases, like water can be liquid or ice or vapor. Our universe might exist in a particular phase of the quantum vacuum. There could be other phases with different physics, different properties. Some theories suggest our vacuum isn't even in the lowest energy state. It's in a metastable state, like supercooled water that could crystallize at any moment. If that's true, our universe could undergo a vacuum phase transition, the current vacuum decaying into a lower energy state, with a bubble of new vacuum expanding at the speed of light, rewriting the laws of physics as it goes. Don't worry. This is purely speculative, and even if true, the timescale would be incomprehensibly long. But it shows how seriously physicists take the idea that the vacuum has structure and properties. Let me bring this back to something more grounded. You're sitting in space right now. Well, you're sitting in a chair in a room, but more fundamentally, you're embedded in the quantum vacuum. And this vacuum isn't empty. It's filled with virtual particles, fluctuating fields, quantum activity. These fluctuations are interacting with the atoms in your body, subtly shifting their energy levels, influencing their properties. You're not separate from the vacuum. You're immersed in it, part of it, constantly interacting with it. Every atom in your body is coupled to the quantum fields that fill all of space. You're connected to the vacuum, and through the vacuum, you're connected to everything else in the universe. Because the quantum fields are everywhere, extending throughout space, linking all matter and energy in a web of field interactions. Isn't that a different way of thinking about existence? You're not an isolated object sitting in empty space. You're a localized excitation of quantum fields, a pattern of energy in the field structure, embedded in a sea of vacuum fluctuations that extends throughout the universe. Your electrons are real particles, but they're constantly interacting with virtual particles. You're half real, half virtual, in a sense. Or rather, the distinction between real and virtual is less clear than classical thinking suggests. This also means the vacuum has energy. Lots of energy, actually. If you calculate the energy density of vacuum fluctuations naively, you get an absurdly large number, something like 10 to the 113 joules per cubic meter. That's more energy in a cubic meter of vacuum than in all the matter in the observable universe. Clearly, that can't be right, or the universe would collapse under its own vacuum energy. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in physics. Why is the observed vacuum energy density so much smaller than what quantum field theory predicts? We don't know. There must be some cancellation mechanism, some reason why most of the vacuum energy doesn't gravitate, but we haven't figured it out yet. What we do know is that the vacuum does have some energy density. We call it dark energy, and it's causing the universe to expand faster and faster. About 68% of the energy in the universe is dark energy, and it might be the energy of the quantum vacuum itself. We're living in a universe dominated by the energy of empty space. How's that for a perspective shift? So when you look out at the night sky, at the vast darkness between stars, you're not looking at emptiness. You're looking at the quantum vacuum, a seething ocean of virtual particles and fluctuating fields, the most abundant form of energy in the universe. The darkness isn't empty. It's the fullest thing there is, and this vacuum is dynamic. Virtual particles pop in and out of existence constantly. Particle-antiparticle pairs appear, exist briefly, and annihilate. Photons fluctuate into existence and vanish. The vacuum is never still, never quiet. It's always humming with activity at scales too small and too fast for us to directly perceive. There's something almost alive about it, don't you think? The vacuum breathes, in a sense. Inhaling virtual particles, exhaling annihilation, constantly creating and destroying right at the edge of existence. The quantum vacuum is the womb of reality, the place where particles can be born, and the place where they return. And here's a final thought to contemplate. Every particle in your body, every electron and quark, might have originated from vacuum fluctuations in the early universe. In the first moments after the Big Bang, the universe was incredibly hot and energetic. Virtual particles were constantly becoming real particles, and real particles were constantly annihilating. In that primordial chaos, some particles survived. Matter survived slightly more than antimatter, for reasons we don't fully understand, and those survivors became everything. The atoms in your body might have started as virtual fluctuations that got promoted to permanent existence. You might be made of crystallized vacuum, patterns of energy that were once temporary, fleeting, virtual, but that somehow became stable, real, lasting. Isn't that beautiful? You're not separate from the vacuum. You emerged from it. You're part of its story. The quantum vacuum isn't empty. It's the foundation of everything. It's the sea in which reality swims, the medium through which forces propagate, the source from which particles emerge. Understanding this changes everything. Space isn't a passive container. It's active, dynamic, full of potential. The void isn't void. It's the richest, most interesting part of the universe. We're moving into deeper waters now, into somewhere that challenges our most fundamental intuition about reality, that the past is fixed, that causality flows forward in time, that what happened yesterday can't be changed by what we do today. Quantum mechanics suggests otherwise, or at least it forces us to reconsider what we mean by the past and what happened. There are experiments, real experiments, performed in laboratories, replicated many times, where a choice made now appears to retroactively change what happened earlier, where the future seems to reach back and rewrite history. This isn't time travel. It's not about sending information backward in time. It's something subtler and, in some ways, stranger. It's about the quantum nature of reality before measurement, and how measurement creates a past as much as it reveals one. Let me start with something you might already know about: the double-slit experiment. It's probably the most famous experiment in quantum mechanics, and for good reason. It encapsulates the weirdness of quantum behavior in one elegant setup. Here's the basic version. You have a light source, a barrier with two slits cut in it, and a screen behind the barrier. You shine light at the slits and observe what pattern appears on the screen. If light were simply particles, little bullets shooting through one slit or the other, you'd expect two bright bands on the screen, one behind each slit. But that's not what happens. What happens is an interference pattern, multiple bright and dark bands alternating, spreading across the screen. This is characteristic of waves. When waves pass through two slits, they spread out, overlap, and interfere. Where two wave peaks meet, you get brightness. Where a peak meets a trough, they cancel out, and you get darkness. The pattern proves that light is behaving as a wave, passing through both slits simultaneously, interfering with itself. But here's where it gets strange. This happens even if you send light one photon at a time. Single photons, arriving one by one, each one an indivisible particle. And yet, over time, they build up an interference pattern. Each photon somehow knows about both slits. It passes through both slits as a wave of probability, interferes with itself, and lands somewhere according to the interference pattern, until you try to determine which slit the photon went through. If you put a detector at one of the slits to check whether the photon passes through that slit, something dramatic happens. The interference pattern disappears. Suddenly, you get two bands, just like particles should make. The photon, caught in the act of being measured, stops behaving like a wave and starts behaving like a particle. It goes through one slit or the other, not both. This is the famous observer effect. Measurement changes what's being measured. When you check which slit the photon uses, you force it to use one slit, and the wave-like interference vanishes. The act of observation determines the behavior. Now, you might think this makes sense in some way. You're measuring the photon as it passes through the slits at that moment, and your measurement affects its behavior from that point forward. The photon reaches the screen as a particle because you measured it as a particle. Past causes future. Normal causality. But in 1978, physicist John Archibald Wheeler proposed a thought experiment that made this much stranger. He asked, what if you delayed the choice? What if you decided whether to measure which slit the photon went through only after the photon had already passed through the slits, after it had presumably already committed to being either a wave or a particle? According to our intuition about time, this shouldn't matter. By the time you make your choice, the photon has already gone through the slits. It's already decided, or the universe has already decided, whether it behaved as a wave or a particle. Your later choice can't change what already happened. but Wheeler predicted it could, and he was right. This is the delayed choice experiment, and it's been performed numerous times with increasingly sophisticated setups. Let me describe how it works in practice. The photon passes through the double slits, but you don't put detectors at the slits. Instead, you set up an arrangement where you can choose, after the photon has passed through the slits, but before it reaches the screen, whether to measure which path information or to allow interference. You can switch between these two configurations very quickly. Faster than light could travel from the slits to your switching mechanism. When you choose to measure which path information, you find that the photon went through one slit or the other, and no interference pattern builds up. When you choose not to measure, you find interference, indicating the photon went through both slits as a wave. The choice you make now determines what the photon did earlier. Or at least, it determines what we can say about what it did earlier. Your decision about what to measure retroactively determines whether the photon behaved as a wave or a particle when it passed through the slits. Does that make you uncomfortable? It should. It violates our deep intuition that the past is fixed. But here's the key insight. Before measurement, the photon isn't in a definite state. It's in a superposition. It's neither definitely a wave nor definitely a particle. It's both, potentially. Only measurement creates a definite reality. And if you delay the measurement until after the photon has passed through the slits, then the nature of reality at the slits remains undefined until you make your delayed choice. The past, at the quantum level, isn't fixed until it's measured, or rather, there are aspects of the past, specifically which path information, that remain in superposition, undefined, until something brings them into definite existence. Your delayed choice doesn't change a pre-existing past. It determines which aspect of a superposed past becomes real. Think of it this way. The photon's history is indeterminate, quantum, existing in multiple possibilities simultaneously. When you finally make a measurement, you collapse not just the photon's present state, but also its past. You select which history actually occurred. But we can go deeper. There's an even stranger version called the quantum eraser experiment, first proposed theoretically and then performed experimentally in the 1990s and 2000s. This experiment shows something that seems impossible. You can erase which path information after the photon has already been detected and retroactively restore the interference pattern. Let me walk you through this carefully because it's genuinely mind-bending. In a quantum eraser setup, photons pass through double slits, and you mark them with which path information. Maybe you use polarization. Photons through the left slit get horizontal polarization. Photons through the right slit get vertical polarization. With this marking, you've determined which slit each photon used, and as expected, the interference pattern vanishes. You get two bands. But, and here's the quantum eraser part, you can later erase this which path information. You can pass the photons through a device that scrambles their polarization, making it impossible to determine which slit they came from. And when you do this, even though the photons have already hit the screen, even though they've already been detected, you find that in the subset where the which path information was erased, the interference pattern reappears. The photons that went through the left slit and the ones that went through the right slit which you carefully marked with different polarizations, suddenly show interference as if they'd gone through both slits simultaneously. But they didn't go through both slits. You know which slit each one used because of the polarization marking. And yet, when you erase that information, interference appears retroactively. How is this possible? The answer lies in quantum entanglement and how we analyze the data. The key is that you have to look at subsets of photons based on what happened to their Witch path markers. When you erase the Witch path information for some photons, those photons, and only those, show interference. The ones where the Witch path information remains don't show interference. So you're not changing what happened. You're revealing different aspects of what happened depending on what measurements you make. The photons were always in a state that contained both possibilities, wave-like and particle-like behavior, entangled with the Witch path markers. Your later choice of whether to erase the markers determines which aspect you see. But doesn't it seem like causality is running backward? You detect the photon, then later you erase the Witch path information, and then you discover that the photon showed interference. Future affecting past. Effect preceding cause. Except, and this is crucial, you can't use this to send information backward in time. You can't change the past in a way that violates causality. Here's why. When you look at the photons hitting the screen, without separating them into subsets based on the eraser measurement, you see no interference. Just a blob. Only when you later perform the eraser measurement and then go back and sort the screen detections based on the eraser results do you see that one subset showed interference and another didn't. So, the interference pattern only becomes visible after you've made the eraser measurement. You can't see it in real time. You have to wait for the information from the future measurement, then retroactively analyze the past data. The future affects how you interpret the past, but it doesn't change it in a way that violates causality. Still, there's something deeply strange here. The photons knew whether their Witch path information would be erased or not, and they behaved accordingly. Photons whose markers would eventually be erased showed interference. Photons whose markers wouldn't be erased didn't show interference. As if information from the future about what measurement you'd perform reached back and affected how the photons behaved. Quantum mechanics is consistent. It doesn't allow for grandfather paradoxes or causal loops, but it does suggest that reality at the quantum level doesn't have a definite past until measurements are made, and that the timing and nature of measurements can determine what past becomes real. Does this mean the past is changeable? Not exactly. It means the past, at quantum scales, before measurement, is in superposition. Multiple pasts exist simultaneously as possibilities. Measurement selects which past is real, which history actually occurred. And this measurement can happen later, delayed, after the event you're determining has already happened in the classical sense. Let me give you an even more extreme version. Wheeler's delayed choice on a cosmic scale. Imagine a quasar, an incredibly bright object billions of light years away. Light from the quasar travels toward Earth. Between the quasar and Earth, there's a massive galaxy. This galaxy's gravity bends light around it, acting as a gravitational lens. Light from the quasar can reach Earth by going around either side of the galaxy. Now, here's the quantum question. Does a single photon from the quasar go around the left side of the galaxy, or the right side, or both? If you set up detectors to determine which side it came from, you'll find it went one way or the other. But if you set up an interference experiment, you'll find interference, indicating it went both ways simultaneously. The photon left the quasar billions of years ago. It traveled through space for eons. The decision about which path it took, one side or both, should have been made billions of years in the past. And yet, what we choose to measure now, today, determines which path it took. Our choice now affects what happened billions of years ago. This isn't just theoretical. Astronomers have observed gravitational lensing from distant quasars. The delayed choice principle applies. The photon's path through space remained in superposition for billions of years until we finally measured it, and our measurement determined which path was real. Do you feel the vertigo of this? The past is not as solid as we thought. At quantum scales, history is fluid, superposed, undetermined, until observation collapses it into definiteness. And this collapse can happen long after the events in question. So, what does this mean for our understanding of time and causality? It means that time at the quantum level doesn't flow the way we think it does. The past doesn't exist independently of measurement. There's no objective history carved in stone. Instead, there are quantum correlations, entangled states, superpositions that extend across time. And measurement, whenever it occurs, collapses these superpositions, selecting which correlations become real, which history becomes actual. This doesn't violate causality in the sense of creating paradoxes. You still can't send information backward in time or change the past in a way that would create contradictions. But it does suggest that our classical notion of time, with a fixed past, a definite present, and an undetermined future, is wrong. At the quantum level, past and future are entangled, interconnected, mutually defining. The physicist John Wheeler put it beautifully. We are participants in bringing into being not only the near and here, but the far away and long ago. Our observations now help determine what happened long ago and far away. We're not passive observers of a pre-existing universe. We're active participants in creating the universe's history through our measurements. And this applies to everything. Every quantum event that hasn't been measured remains in superposition, its history undetermined. Only through the web of measurements and interactions does definite history emerge. The past, in this view, is constantly being created by the present, shaped by observation, crystallizing out of quantum possibility into classical reality. Isn't that a strange and beautiful thought? You're not just moving forward through time, observing what exists. You're collapsing superpositions, determining which pasts are real, participating in the creation of history itself. Every measurement you make, every observation, every interaction, it's all helping to define what was, is, and will be. The delayed choice and quantum eraser experiments show us that the universe is more interconnected across time than we imagined. Past, present, and future aren't separate realms. They're entangled, quantum correlated, mutually dependent. The future doesn't just depend on the past. The past, in some sense, depends on the future, or rather, both depend on the measurements that collapse superpositions into definite reality. And this is just one aspect of quantum mechanics' strangeness. We haven't even talked about entanglement yet, about how particles separated by vast distances can remain mysteriously connected, how measuring one instantly affects the other, regardless of the distance between them. That's where we're heading next, into the deep weirdness of quantum correlations, into what Einstein called spooky action at a distance. And I want to be clear from the start, entanglement is probably the most misunderstood phenomenon in quantum mechanics. It's been wrapped in mysticism, used to justify all sorts of pseudoscience, and generally made to sound more magical than it is. But the reality, the actual physics, is strange enough without embellishment. Stranger, in fact, than most of the mystical interpretations give it credit for. Let me start with what entanglement isn't. It's not telepathy. It's not a way to send information faster than light. It's not proof that everything is connected in some vague spiritual sense. Those are misunderstandings, misapplications of quantum mechanics to realms where it doesn't apply. But here's what entanglement is. Two particles, or more, can be created or interact in such a way that their quantum states become correlated. Not just correlated in the classical sense of, if this one is X, that one is probably Y, but correlated in a deeper, stranger way, a quantum way. The particles don't have definite individual states until measured, but once you measure one, you instantly know something about the other, regardless of the distance between them. Let me give you a specific example. Imagine you create two photons in a process that ensures they have opposite polarizations. If one is horizontally polarized, the other is vertically polarized. You send these photons in opposite directions, one to your left, one to your right. They travel far apart, maybe meters, maybe kilometers, maybe light years. Now, before you measure them, quantum mechanics says neither photon has a definite polarization. Each exists in a superposition of horizontal and vertical, but they're not in independent superpositions. They're entangled. The full quantum state isn't photon A is in superposition and photon B is in superposition. It's more like if photon A is horizontal, then photon B is vertical. And if photon A is vertical, then photon B is horizontal. Both possibilities existing simultaneously. When you measure photon A and find it's horizontally polarized, photon B's state instantly becomes vertically polarized. Not was always vertically polarized, but we didn't know it. Actually becomes. The measurement of A collapses not just A's wave function, but also B's wave function instantaneously, regardless of the distance between them. Einstein hated this. He really did. In 1935, along with Boris Podolsky and Nathan Rosen, he published a paper known as the EPR paper after their initials, arguing that this couldn't be how reality works. His reasoning went like this. Either information is traveling faster than light between the particles, which violates relativity, or the particles had definite states all along, and quantum mechanics is just incomplete. Einstein preferred the second option. He imagined there might be hidden variables, properties of particles that quantum mechanics doesn't describe, but that determine measurement outcomes. The particles aren't really in superposition, he argued. They have definite states from the moment they're created. We just don't know what those states are until we measure them. The correlation we observe is like having two envelopes with opposite messages. Open one and find red, and you instantly know the other says blue. But that doesn't mean the messages were undefined until you open the envelopes. They were always determined. You just didn't know. This seemed reasonable, classical, sensible. And for decades, it was thought that maybe Einstein was right, that quantum mechanics was missing something, that hidden variables could explain everything without spooky action at a distance. But in 1964, physicist John Stuart Bell proved something remarkable. He showed mathematically that local hidden variables that respect the speed of light limit, make predictions that differ from quantum mechanics. He derived an inequality, now called Bell's inequality, that any local hidden variable theory must satisfy, and quantum mechanics violates this inequality. This was profound. Bell showed that you could experimentally test whether the universe operates according to local hidden variables or according to quantum mechanics. You could settle the debate. The universe itself would tell you which view is correct. And then, over subsequent decades, physicists performed these tests. Alain Aspect, in the 1980s, did groundbreaking experiments. Many others followed, improving precision, closing loopholes, ruling out alternative explanations. And consistently, overwhelmingly, the results violate Bell's inequality. The predictions of quantum mechanics are confirmed. Hidden variables don't work. This means, and let this sink in, that entangled particles genuinely don't have definite states until measured. The correlation isn't because they were programmed with opposite values from the start. It's because they exist in a genuinely shared quantum state, a superposition that spans across space, connecting them in a way that has no classical analog. When you measure one particle, you're not just learning about its state. You're collapsing a superposition that includes both particles. And this collapse happens instantaneously, regardless of distance. The measurement here affects the state there, faster than light could travel between them. But, and this is crucial, you can't use this to send information. Here's why. When you measure your photon, you get a random result, horizontal or vertical, with probabilities determined by the quantum state. You can't control which outcome you get. On the other side, when your partner measures their photon, they also get a random result. Only when you later compare measurements do you find the correlation. Every time you got horizontal, they got vertical, and vice versa. So neither person sees anything unusual in their individual measurements, just random outcomes. The correlation only appears when you bring the two sets of results together and compare them. And bringing results together requires classical communication, which is limited by the speed of light. No faster-than-light messaging. No violation of relativity's prohibition on superluminal information transfer. But the correlations themselves, those are non-local. They happen instantaneously. The universe maintains these quantum correlations across arbitrary distances, updating them simultaneously when measurements occur. Space, in some sense, doesn't separate entangled particles. They're part of a single quantum system, no matter how far apart they are. Do you feel the strangeness of this? The universe has a way of maintaining correlations that transcend space. Two particles, light years apart, can be in a single quantum state, such that measuring one instantly affects the other. Not by sending a signal, that would take years. By being fundamentally, irreducibly connected in a way that doesn't require signals or communication or any mediating influence. This forced physicists to reconsider what we mean by separate objects. In classical physics, separation means independence. Two objects far apart don't affect each other, except through forces that propagate at finite speed. But in quantum mechanics, entangled objects aren't truly separate. They're part of a single quantum system. Distance doesn't break the entanglement. And entanglement isn't rare or fragile. It's actually quite common. Whenever particles interact, they typically become at least slightly entangled. The photons scattered off your body right now are probably entangled with atoms in your skin. The air molecules bouncing around you are entangled with each other and with surfaces they've touched. Entanglement is ubiquitous. The challenge is maintaining strong entanglement, keeping it coherent and usable. Because as we learned with decoherence, interactions with the environment tend to destroy quantum correlations. Entangled particles interacting with their surroundings become entangled with the environment instead, and the original entanglement gets diluted, scrambled, effectively lost. That's why quantum experiments require careful isolation. You can't just entangle two particles and separate them by kilometers in open air. The air would interact with them, decohering them, destroying the entanglement. You need vacuum, or fiber optic cables, or some way to protect the particles from environmental interaction. It's technically challenging, but entirely possible. Physicists routinely create and maintain entanglement over long distances now. In fact, there's an entire technology emerging based on entanglement, quantum communication, and quantum cryptography. The idea is to use entangled particles to share encryption keys. If someone tries to intercept the key, they have to measure the particles, which collapses the entanglement and introduces detectable errors. You can create communication channels that are fundamentally secure, protected by the laws of quantum mechanics rather than mathematical complexity. China launched a quantum communication satellite called Mikius in 2016 that distributes entangled photons to ground stations over 1,000 kilometers apart. Quantum networks are being built. Entanglement is moving from laboratory curiosity to practical technology. The strangeness is becoming useful. But let's return to the deeper question. What does entanglement tell us about reality? I think it tells us something profound about the nature of objects and properties. In classical thinking, objects have definite properties independent of observation. The ball is red even when no one's looking. The electron has a specific spin even before you measure it. Properties belong to objects, but entanglement suggests otherwise. Entangled particles don't have definite individual properties. Only the combined system has a definite state. The properties aren't in the particles. They're in the relationships between particles. Reality is relational rather than absolute. This is a radical shift in perspective. It means that objects aren't self-contained, independent things with intrinsic properties. They're nodes in a web of quantum correlations. Their properties emerge from their relationships, from their entanglements with other systems. separate an entangled particle from its partner, and it doesn't have definite properties, just correlations waiting to be realized through measurement. Some physicists and philosophers take this even further. They suggest that entanglement implies a kind of holism, that quantum systems can't be understood by looking at parts in isolation. The whole is more than the sum of parts. It's fundamentally, irreducibly more. Properties belong to the whole system, not to individual components. This is hard to wrap your mind around, I know. We're so used to thinking of objects as separate, independent, with their own properties. A rock is a rock, with definite mass, shape, composition, whether or not it's interacting with anything else. But at the quantum level, this picture breaks down. Particles are entangled, interconnected, defined by relationships rather than intrinsic properties. And remember, everything is quantum at its core. Rocks, chairs, people, we're all made of quantum particles. The classical appearance, the sense of having definite properties independent of observation, emerges from decoherence and the averaging of countless quantum interactions. But underneath, we're entangled with our surroundings, our particles correlated with environmental particles, our quantum states extended beyond our apparent boundaries. You're entangled with the air around you, with the light bouncing off you, with the earth beneath you. Not strongly enough for the entanglement to be measurable. Decoherence ensures that. But it's there, in principle. You're not as separate from the world as you feel. You're part of a vast web of quantum correlations extending throughout space. And this connects back to what we discussed about the quantum vacuum. The vacuum is filled with entangled quantum fluctuations. Virtual particle pairs pop into existence, entangled with each other, and then annihilate. The quantum fields permeating space are correlated with each other. The universe is, at the quantum level, a single interconnected system, a web of entanglements spanning space and time. When physicists calculate the entropy of black holes, the amount of information they contain, they find it's proportional to the surface area of the event horizon, not the volume. This suggests that information in the universe might be fundamentally holographic, stored on surfaces rather than in volumes. And this holographic principle is deeply connected to entanglement. The way quantum information is distributed through entanglement might be what gives rise to the structure of space-time itself. Some theorists even propose that space-time emerges from entanglement, that space and distance are not fundamental, but arise from patterns of quantum correlation. When particles are strongly entangled, they're close in an emergent spatial sense. When entanglement is weak, they're far apart. In this view, space itself is a macroscopic manifestation of microscopic quantum entanglements. This is speculative, cutting-edge theoretical physics. We don't know if it's true, but the fact that it's even being seriously considered shows how profound entanglement is. It's not just a weird quantum effect. It might be the fundamental feature of reality from which everything else emerges. Let me bring this back to something concrete, something you can almost touch. When you look at a star at night, photons that left that star years ago are entering your eye. These photons have traveled across space, through the vacuum, maintaining their quantum properties. When they hit your retina, they interact with molecules in your eye, triggering chemical reactions that lead to electrical signals in your neurons. In that moment of interaction, the photon and the molecule become briefly entangled. The photon state influences the molecule's state, and vice versa. Then decoherence quickly takes over. The entanglement spreads into the environment and gets lost. But for a brief moment, you, or at least molecules in your eye, were quantumly entangled with that distant star. There's something poetic about that, isn't there? You're not just observing the universe from a distance. You're becoming briefly entangled with it, forming quantum connections with distant objects, participating in the web of correlations that constitutes reality. Every observation is a moment of connection, of entanglement. Before, decoherence separates you back into apparent isolation. And perhaps this gives us a different way to think about ourselves and our place in the universe. Not as isolated observers, separate from what we observe, but as participants, connected, entangled, part of the quantum whole. The boundaries we perceive between self and world, between here and there, between past and future. These are classical approximations. Underneath, at the quantum level, everything is interconnected through entanglement. Einstein was wrong to call it spooky action at a distance. It's not action at a distance. It's action without distance. Entangled particles aren't affecting each other across space. They're part of a single system that transcends spatial separation. Distance is a classical concept that doesn't fully capture quantum reality. In this non-local nature of quantum correlations, confirmed by decades of experiments violating Bell's inequalities, tells us something deep about the universe. It tells us that reality is fundamentally interconnected in ways that transcend space and time. That separateness is emergent, approximate, not fundamental. That we live in a universe that is, at its quantum core, a unified whole. This doesn't mean everything affects everything else directly. Most entanglements are weak, quickly destroyed by decoherence. The universe isn't a mystical unity where your thoughts affect distant galaxies. But it does mean that the fabric of reality is woven from quantum correlations, that information is shared non-locally, that the universe maintains connections that our classical intuitions can't fully grasp. And we're still discovering new implications of entanglement, new ways it manifests, new technologies it enables. Quantum computers rely on entanglement to perform calculations impossible for classical computers. Quantum teleportation, where the quantum state of one particle is transferred to another using entanglement, has been demonstrated experimentally. The quantum internet, connecting quantum computers through entangled channels, is being developed. The strangeness Einstein rejected is becoming the foundation of new technologies, new ways of processing and transmitting information. The universe's quantum nature, its non-local correlations, its fundamental interconnectedness, these aren't obstacles to understanding. They're features we're learning to use, to leverage, to build with. We've explored entanglement, how quantum particles remain mysteriously connected across space, how the universe maintains correlations that transcend distance. Now, I want to show you something that might seem impossible even by quantum standards. Something so counterintuitive that when it was first proposed, even physicists who were comfortable with quantum weirdness found it hard to believe. It's called the quantum pigeonhole principle, and it involves a situation that seems to violate basic logic itself. Not just our intuitions about particles or waves or measurement, but the fundamental logic of counting, of how objects occupy space, of the pigeonhole principle that we learn in elementary school. Let me remind you of the classical pigeonhole principle first. It's beautifully simple, almost trivially obvious. If you have 3 pigeons and 2 pigeonholes, then at least 2 pigeons must be in the same hole. There's no way around it. You can't fit 3 distinct objects into 2 distinct containers without at least one container holding more than one object. This is logic, mathematics, truth by pure reason. Except in quantum mechanics, it's not true. You can arrange 3 quantum particles in 2 boxes in such a way that no 2 particles are ever in the same box. Somehow, impossibly, 3 particles occupy 2 boxes without any box containing more than one particle. The quantum pigeonhole principle is violated. How? How is this possible? Let me walk you through this slowly, because it's genuinely strange, and I want you to understand not just that it happens, but how it can happen without violating logic or mathematics. The key, as with so much in quantum mechanics, is measurement, and what we mean by a particle being in a box. In classical thinking, a particle is either in box A or in box B. These are definite, mutually exclusive states. Check the boxes, and you'll find the particle in one or the other. Count up all the particles, and if you have 3 particles and 2 boxes, at least one box must contain at least 2 particles. But quantum particles can be in superpositions. A particle can be in a state that's simultaneously in box A and in box B, until you measure which box it's in. And this is crucial. You can create quantum states where 3 particles are arranged such that measuring whether any 2 specific particles are in the same box always gives the answer no, even though there are only 2 boxes. Let me give you a concrete example, discovered theoretically in 2014 by Yakir Aharonov and colleagues, and then demonstrated experimentally. You have 3 particles. Let's call them particles 1, 2, and 3, and 2 boxes, A and B. You prepare the particles in a specific entangled quantum state. Now, you perform measurements. Not measurements of where each particle is individually. That would force them into definite locations, and you'd get the classical pigeonhole result. Instead, you measure whether particle 1 and particle 2 are in the same box. The answer comes back, no, they're in different boxes. You measure whether particle 1 and particle 3 are in the same box. Again, no, different boxes. You measure whether particle 2 and particle 3 are in the same box. Once more, no, different boxes. So particle 1 and 2 are in different boxes, and particle 1 and 3 are in different boxes, and particle 2 and 3 are in different boxes. But there are only 2 boxes. How can all 3 pairs be in different boxes if there are only 2 boxes total? If particle 1 is in box A, then particles 2 and 3 must both be in box B, to be in different boxes from particle 1. But then particles 2 and 3 would be in the same box, contradicting our measurement. The logic seems to break down. The measurements appear to describe an impossible situation, and yet this has been demonstrated experimentally. Physicists have created these quantum states and performed these measurements. The results are exactly as predicted by quantum mechanics. 3 particles, 2 boxes, no 2 particles in the same box. What's happening? The resolution lies in understanding what quantum measurements actually tell us. When you measure whether particles 1 and 2 are in the same box, you're not learning where particle 1 is and where particle 2 is separately. You're learning about a joint property, the sameness or differentness of their locations. These joint measurements don't force individual particles into definite locations. They only constrain the correlations between particles. The quantum state is arranged so that all pairwise correlation measurements show different boxes. But this doesn't mean the particles have individual locations that satisfy all these constraints simultaneously. There is no classical configuration, no assignment of particles to boxes that matches the measurement results. The particles are in a genuinely quantum state that has no classical analog. Think about it this way. In classical logic, properties belong to individual objects. Each pigeon is in a specific hole. But in quantum mechanics, properties can be relational, belonging to pairs or groups rather than individuals. The quantum state doesn't specify where particle 1 is, where particle 2 is, and where particle 3 is. It specifies correlations. Particle 1 and 2 are different. Particle 1 and 3 are different. Particle 2 and 3 are different. These correlations don't arise from individual locations. They're fundamental properties of the entangled state. Does this make you dizzy? It should. We're confronting the limits of classical logic when applied to quantum systems. The pigeonhole principle, which seems like pure mathematics, independent of physics, turns out to depend on classical assumptions about how properties work. Remove those assumptions, allow quantum superposition and entanglement, and even logic becomes negotiable. But wait, you might ask, doesn't this lead to contradictions? If you can violate the pigeonhole principle, can you prove that 2 plus 2 equals 5? Can you derive logical paradoxes? No. And here's why. You can never simultaneously measure the individual locations. If you try to measure where particle 1 is, you collapse its superposition, forcing it into a definite box. This measurement affects the quantum state, changing the correlations. Once you've pinned down individual locations, the quantum weirdness disappears, and you're back to classical pigeonhole logic. The violation only appears when you measure joint properties without measuring individual properties. It's a consequence of the quantum mechanical fact that you can't measure everything simultaneously, that observing one aspect of a system prevents you from observing complementary aspects. This connects to something deeper, the nature of reality before measurement. The quantum pigeonhole principle shows that particles don't have definite locations before measurement, not even in principle. There's no true assignment of particles to boxes that the measurements are revealing. The measurements are creating correlations, not discovering pre-existing ones. In classical physics, measurement reveals reality. You measure where the particle is, and you learn where it was before you measured. But in quantum mechanics, measurement participates in creating reality. Before measurement, particles don't have definite locations. They have potential locations, correlated in strange ways, existing in superpositions that can violate classical logic. The quantum pigeonhole principle is a particularly stark demonstration of this. It shows that you can't think of quantum particles as having trajectories, definite positions at each moment in time, even if you're not observing them. The particles don't secretly have definite locations that happen to conspire to give weird measurement results. They genuinely don't have definite locations until measured. And this has been experimentally verified. In 2016, a team of physicists performed a version of this experiment using the paths of photons. They created situations where 3 photon paths were distributed among 2 potential locations, and measurements showed that no 2 paths overlapped, even though there were only 2 locations. The quantum pigeonhole principle was violated, just as theory predicted. What does this mean for our understanding of reality? It reinforces something we've encountered repeatedly. Quantum objects don't have all properties defined simultaneously. Before measurement, they exist in states of potentiality, with some properties definite and others indefinite. And crucially, which properties are definite depends on how the state was prepared and what measurements you choose to perform. This is sometimes called contextuality. The properties of quantum systems depend on the context, the measurement setup, the history of interactions. You can't assign definite values to all properties simultaneously in a way that's independent of measurement context. Properties emerge through measurement, not just are revealed by it. The quantum pigeonhole principle is an extreme example of this contextuality. The particles are in a state where pairwise relationships are well defined, but individual locations are not. Ask about pairs, and you get consistent answers that violate classical pigeonhole logic. Ask about individuals, and you collapse the state into something classical. There's something philosophically profound here. We're used to thinking that relationships between objects are determined by properties of the individual objects. 2 balls are far apart because ball A is at location X and ball B is at location Y, and X and Y are far apart. The relationship derives from the individual properties, but quantum mechanics allows relationships to be primary. Particles can have definite relational properties. These 2 are different, without having definite individual properties. The correlation exists without the individual values that would classically give rise to it. This might sound abstract, but it's experimentally real, and it points to a deeper truth about quantum mechanics. The world is fundamentally relational. Properties don't reside in objects. They reside in interactions, in measurements, in the relationships between systems. An electron doesn't have a definite spin. It has a spin relative to a measurement axis. 2 particles don't have definite locations. They have a definite relationship. same box or different box, that doesn't reduce to individual locations. And this is universal. Everything in the quantum world operates this way. The appearance of definite individual properties, classical reality, emerges through decoherence, through the environment constantly measuring everything, forcing quantum systems into definite states through interaction. But underneath, fundamentally, reality is relational, contextual, dependent on measurement. You might wonder, does this apply to everyday objects? To pigeons and pigeonholes? Could you actually observe this with real birds? No. The quantum pigeonhole effect requires maintaining quantum coherence across three particles in a carefully prepared, entangled state. Any interaction with the environment, light bouncing off the particles, air molecules colliding with them, would cause decoherence, destroying the delicate quantum correlations and reducing everything to classical behavior. Real pigeons are made of something like 10 to the 26 atoms each, all constantly interacting with their environment. There's no way to maintain quantum coherence at that scale. The quantum weirdness gets washed out immediately by decoherence, and you're left with classical pigeonhole logic. But for individual quantum particles, carefully isolated from their environment, the effect is real. And it shows us something important. The classical logic we rely on, the logic that seems self-evident and universal, is actually an approximation. It works beautifully at large scales where decoherence dominates. But at the quantum level, reality operates by different rules. This doesn't mean quantum mechanics is illogical. It means our intuitive logic, developed from experience with macroscopic objects, doesn't fully capture quantum reality. Quantum mechanics has its own consistent mathematical structure, its own logic. It's just not the Boolean logic of everyday experience. And physicists are developing new logical frameworks to capture quantum behavior. Quantum logic, where propositions don't obey all the classical rules. Topos theory, where you can have multiple contexts with different truths in each context. These are attempts to find the right mathematical language for quantum reality, to go beyond classical assumptions and embrace the strangeness. The quantum pigeonhole principle is one more piece of evidence that we need these new frameworks. It shows that you can't describe quantum reality using classical concepts like, this particle is in this box. You need a richer description that accounts for superposition, entanglement, contextuality, all the features that make quantum mechanics quantum. And yet, despite all this strangeness, quantum mechanics works. It makes predictions, and those predictions are confirmed by experiment with extraordinary precision. The quantum pigeonhole principle isn't a bug or a contradiction. It's a feature of reality, a consequence of how the universe actually operates at fundamental scales. There's something liberating about this, I think. The universe isn't constrained by our intuitions about how things should work. It's not limited by classical logic or everyday experience. It's stranger, richer, more surprising than we imagined. 3 particles in 2 boxes with no 2 together isn't impossible. It's just quantum. And this strangeness, this violation of classical expectations, isn't confined to abstract particle physics. It's showing up in real systems, in potential technologies. Quantum computers exploit exactly this kind of contextuality. This ability of quantum systems to be in states that have no classical analog. The weirdness is becoming useful. As we continue exploring quantum mechanics, we're going to see more of this pattern. Phenomena that seem impossible by classical standards, that violate our deepest intuitions, but that are nevertheless real, experimentally verified, part of the fabric of reality. The quantum world doesn't care about our expectations. It operates by its own rules, rules that we're still learning, still trying to fully understand. And perhaps that's the deepest lesson of the quantum pigeonhole principle. Reality is under no obligation to make sense to us. It doesn't have to conform to our logic, our intuitions, our expectations about how things should work. The universe is what it is, in all its quantum strangeness. And our job isn't to force it into classical boxes, to insist that three pigeons must share a hole because logic demands it. Our job is to observe, to measure, to calculate, and to accept what the universe tells us, no matter how strange it seems. Three particles in two boxes with no two together. It sounds impossible. It violates elementary logic. And yet, in the quantum world, it's just another day, just another demonstration that reality is far stranger and more wonderful than our classical minds can easily grasp. Now, I want to bring quantum mechanics somewhere you might not expect, into the messy, warm, wet world of living things, into cells and chloroplasts, into bird eyes and enzyme active sites, into the very machinery of life itself. For most of the 20th century, physicists and biologists thought quantum effects couldn't possibly matter in biology. Life happens at room temperature, in aqueous solutions, surrounded by countless molecules, all jostling and colliding. This is exactly the kind of noisy, interactive environment that causes decoherence. The same decoherence we've discussed that destroys quantum superpositions and makes the world look classical. Quantum mechanics, physicists thought, required cold temperatures, high vacuum, careful isolation. It was for physics labs, not living cells. Biology operated by classical rules, molecular shapes fitting together like locks and keys, chemical reactions following classical thermodynamics, information encoded in the sequences of DNA bases. Quantum mechanics might govern the electrons in individual atoms, sure, but nothing important at the level where life operates. Except they were wrong. Over the last few decades, evidence has accumulated that life not only tolerates quantum effects, it exploits them. Evolution, that blind watchmaker, that optimizer with billions of years to experiment, has apparently discovered how to harness quantum mechanics. And in some cases, living systems maintain quantum coherence better than human-engineered quantum devices. We touched on some of this earlier: photosynthesis, bird navigation, possibly olfaction. But now let's go deeper. Let's explore what it means that life might be, in part, a quantum phenomenon. Start with photosynthesis, because it's the most well-established case of quantum biology. Plants, algae, and photosynthetic bacteria capture sunlight with near-perfect efficiency, sometimes exceeding 95%. This is extraordinary. Photons hit chlorophyll molecules, creating excitons, quantum packets of excitation energy. These excitons need to travel through a complex of proteins and chromophores to reach the reaction center where chemistry happens. Classically, you'd expect the exciton to take a random walk, bouncing around, possibly getting lost or dissipated as heat. The efficiency should be much lower than observed. But in 2007, researchers at UC Berkeley used ultrafast laser spectroscopy to observe what actually happens. And they found something shocking: quantum coherence. The exciton exists in a superposition of being in multiple places simultaneously, exploring multiple pathways at once, like a wave interfering with itself. This coherence lasts for hundreds of femtoseconds. That's hundreds of quadrillionths of a second. It sounds brief, but it's long enough. Long enough for the exciton to quantum mechanically explore the energy landscape, to find the most efficient path through quantum interference. The exciton is essentially performing a quantum computation, solving the problem: which path gets me to the reaction center fastest, by trying all paths in superposition. And this happens at room temperature, in a wet, noisy, biological environment. The photosynthetic complex has somehow evolved a structure that protects quantum coherence just long enough for it to be useful. The protein scaffold, the specific arrangement of molecules, the vibrational modes of the system, all of it conspires to enable quantum effects that shouldn't be possible under those conditions. Since that initial discovery, similar quantum coherence has been found in various photosynthetic organisms. It's not unique to one species. It appears to be a general feature of photosynthesis, refined by hundreds of millions of years of evolution. Life discovered quantum computing before humans did. But how? How does a warm, wet cell maintain quantum coherence when our best quantum computers require near absolute zero temperatures? The answer seems to involve something called environment-assisted quantum transport. The environment, the protein vibrations, the thermal fluctuations, isn't just noise destroying coherence. It's structured noise that actually helps guide the quantum process. The environment and the quantum system are coupled in a way that preserves just enough coherence for the system to work, while preventing the exciton from getting trapped in local energy minima. It's like walking through a forest in fog. The fog obscures your view, but it also reveals the paths. Light filters through certain directions, guiding you even as it limits visibility. The biological environment does something similar for quantum systems, providing structured noise that guides rather than destroys. Then there's bird navigation, which we mentioned earlier but is worth revisiting. Many bird species migrate thousands of miles with remarkable precision, somehow sensing Earth's magnetic field. For decades, scientists couldn't figure out how. The magnetic field is incredibly weak, about 0.5 Gauss at Earth's surface. There's no known biological magnetometer sensitive enough to detect such weak fields using classical physics. But in the 1970s, Klaus Schulten proposed a radical idea. Birds use quantum entanglement. In birds' eyes, there are proteins called cryptochromes. When light hits these proteins, it can create radical pairs of molecules with unpaired electrons. These electron spins become entangled. Here's the quantum part. Earth's magnetic field, though weak, is strong enough to affect the evolution of entangled electron spins. Different alignments of the bird relative to the magnetic field produce different quantum states of the radical pairs. These different quantum states lead to different chemical products. The bird's visual system can detect these chemical differences, effectively seeing the magnetic field overlaid on their visual field. For years, this was just a hypothesis, but experimental evidence has accumulated. Researchers have shown that disrupting cryptochromes disrupts bird navigation. They've demonstrated that magnetic field effects on radical pair reactions are consistent with what's needed for navigation. They've even shown that radio frequency fields, which would disrupt quantum coherence, interfere with birds' ability to navigate. Migratory birds appear to be using quantum entanglement to see magnetic fields. Your backyard robin, heading south for winter, is exploiting spooky action at a distance. Evolution discovered quantum sensing. And this quantum compass works at body temperature, in bright daylight, in the complex chemical environment of a living cell. Again, biology is doing what human technology struggles to do, maintaining quantum coherence under challenging conditions. Now, enzyme catalysis. Enzymes are proteins that speed up chemical reactions, sometimes by factors of 10^15 or more. They're absurdly good at what they do. A reaction that would take thousands of years without an enzyme happens in milliseconds with one. How? Part of the answer is classical. Enzymes bind substrates, bring molecules together in the right orientation, stabilize transition states. But that doesn't fully explain the extraordinary rate accelerations observed. There's mounting evidence that quantum tunneling plays a crucial role. Remember quantum tunneling, particles passing through energy barriers they shouldn't classically be able to cross. In enzyme reactions, this often involves hydrogen atoms or protons tunneling from one molecule to another. The enzyme creates a geometry where the tunneling distance is minimized, dramatically increasing the tunneling probability. Studies have shown that hydrogen transfer rates in enzymes are too fast to be explained by classical barrier crossing. They show temperature dependence patterns consistent with quantum tunneling. When researchers replace hydrogen with deuterium, a heavier isotope, reaction rates drop more than classical chemistry predicts, exactly as quantum tunneling theory suggests. So, your cells are using quantum tunneling for basic metabolism. The ATP synthase spinning in your mitochondria right now, generating energy for your cells, might be exploiting quantum effects. Quantum mechanics isn't just happening in your body, it's enabling your body to function. And then there's DNA, the molecule that encodes your genetic information, that makes you you. DNA mutations are often attributed to random chemical errors, cosmic rays, environmental damage. But there's evidence that quantum effects might play a role in how mutations occur, and possibly even how they're prevented. Protons can tunnel between DNA base pairs. A proton in the hydrogen bond holding two bases together can tunnel from one side to another, temporarily creating a tautomer, an alternative form of the base. If DNA replicates while in this alternative form, you get a mutation. Quantum tunneling might be a source of genetic variation, the raw material for evolution. Some researchers have even proposed that quantum error correction might occur in DNA. Just as quantum computers need error correction to maintain coherence, perhaps biological systems have evolved quantum error correction mechanisms to protect genetic information. This is highly speculative, but it shows how seriously scientists are taking quantum effects in biology. Then there's consciousness, that hardest of hard problems. We mentioned earlier the Penrose-Hameroff theory that consciousness might involve quantum processes in microtubules inside neurons. Most neuroscientists are skeptical. The brain seems too warm, too noisy for delicate quantum coherence. Neurons operate through electrical spikes and chemical neurotransmitters, all very classical. But here's the thing. Photosynthesis seemed too warm and noisy for quantum coherence too, until we measured it. Bird brains seemed too messy for quantum entanglement, until evidence accumulated. Maybe the brain is also doing something we haven't fully understood yet. The Penrose-Hameroff proposal is that microtubules, structural proteins forming part of the cellular skeleton, can exist in quantum superpositions. These superpositions could, in theory, perform quantum computations related to consciousness. When the superposition reaches a certain threshold, it undergoes objective collapse, and this collapse corresponds to a moment of conscious experience. This is controversial. There's no direct evidence yet, but it's worth noting that microtubules are highly ordered structures, cylindrical protein lattices with interesting properties. They're not just random cellular components. They conduct electrical signals. They're involved in information processing. They're affected by anesthetics, drugs that eliminate consciousness. And there's some evidence that anesthetics might work by disrupting quantum processes. Anesthetics are diverse molecules with little obvious chemical similarity, yet they all produce unconsciousness. One theory is that they all affect quantum coherence in some way, perhaps in microtubules or lipid membranes. When quantum coherence is disrupted, consciousness ceases. Again, this is speculative, but the point is that it's now reasonable to ask these questions, to seriously investigate whether quantum effects play a role in consciousness. A few decades ago, this would have been dismissed out of hand. Now, given what we've discovered about quantum biology, it's worth investigating. Whether or not consciousness is quantum, there's no doubt that quantum effects are important in biology, and this changes how we think about life itself. Life isn't just classical chemistry. It's at the boundary between quantum and classical, exploiting quantum effects where useful while maintaining enough decoherence to be stable. Think about what this means. You're not just a classical machine, a biological computer running deterministic programs. You're a quantum system, maintaining pockets of coherence amid decoherence, exploiting tunneling and superposition and possibly entanglement for basic biological functions. The line between quantum and classical runs through you, through every cell, through the very processes that keep you alive. And evolution found this boundary. Through blind variation and selection over billions of years, life discovered how to harness quantum mechanics. Not by understanding it, evolution doesn't understand anything, but by randomly stumbling upon molecular structures that happen to work better because they exploited quantum effects, and then refining those structures through countless generations. The photosynthetic complexes that maintain quantum coherence, evolution built them, atom by atom, without knowing why they worked, just that they worked better than alternatives. The cryptochromes in bird eyes that use entanglement, evolution shaped them through millions of years of migration. favoring any random mutation that improved navigation even slightly. Life is a quantum engineer, perhaps the best quantum engineer in the known universe. And it achieved this without consciousness, without understanding, without design, just through the patient, relentless optimization of natural selection. What else might life be doing with quantum mechanics that we haven't discovered yet? Are there quantum effects in the brain we haven't measured? In embryonic development? In the immune system? The more we look, the more quantum biology we find. It's a young field, still full of surprises, and it suggests something profound. The boundary between quantum and classical isn't a sharp line. It's a gradient, a zone where both quantum and classical rules apply. And life exists in that zone, that twilight region where quantum effects are possible but not dominant, where superpositions can survive for femtoseconds or picoseconds before decoherence takes over, where that brief moment of coherence is enough to make the difference between life and chemistry. You're living in that twilight zone right now. Your cells are exploiting quantum effects at this very moment. Photons hitting your retina are being processed by molecules that might use quantum mechanisms. Electrons in your cellular machinery are tunneling through barriers. Your body is warm and classical on the surface, but quantum at its heart. And this connects to everything we've been discussing. The quantum vacuum seething with virtual particles. You're made of structures that emerged from that vacuum. The wave-particle duality, light hitting your eyes, behaves as both. The uncertainty principle. Your neurons operate at energy scales where quantum fluctuations might matter. Entanglement. Molecules in your cells might be exploiting it for sensing and navigation. You're not separate from quantum mechanics. You're immersed in it, made of it, possibly exploiting it to live and think and be. The quantum world isn't elsewhere, in physics labs or deep space. It's here, in you, enabling your existence through mechanisms evolution discovered long before humans ever conceived of quantum theory. And perhaps this gives us a different perspective on life itself. Life isn't just complex chemistry. It's matter organized in ways that can exploit the boundary between quantum and classical, between superposition and definiteness, between coherence and decoherence. Life is quantum mechanics learning to use itself, to create structures that can harness quantum effects for survival and reproduction. This is still being discovered, still being understood. Quantum biology is frontier science, with new findings emerging regularly. We don't yet know of the full extent of quantum effects in living systems, but we know enough to say, life is quantum, at least in part. And that's extraordinary. It means you're more than classical physics can describe. Your existence involves phenomena that puzzled Einstein, that violate classical intuitions, that exist at the strange boundary where the quantum world meets the everyday world. You're a walking, thinking example of quantum mechanics in action, a biological system that evolution has refined over billions of years to exploit the deepest features of physical reality. And as we continue exploring quantum mechanics, as we delve into the interpretation questions, the measurement problems, the deep puzzles about what quantum mechanics means, remember this: whatever the answer is, it has to account for you, for life, for the fact that quantum effects aren't just abstract physics, but are woven into the fabric of living things. The quantum world isn't separate from the biological world. They're the same world, the same reality, just viewed at different scales and different contexts. And you exist at the intersection, a quantum biological system contemplating the quantum nature of your own existence. That's beautiful. That's profound. And that's you right now, in this moment, being both quantum and classical, both particle and wave, both definite and uncertain, both separate and entangled with everything around you. So here we are, at the end of our journey through the quantum world. Before you go, if this journey has brought you some peace, some wonder, some quiet appreciation for the strangeness of existence, I'd be grateful if you'd subscribe to The Gentle Scientist. Leave a like if these ideas resonated with you. And perhaps, in the comments, you could share what surprised you most tonight, or what you're still contemplating as you drift towards sleep. Your thoughts, your questions, your wonder, they're part of this conversation, this collective exploration of reality's deepest nature. Thank you for spending this time with me. The universe is vast and mysterious and fundamentally uncertain, and you're a beautiful part of that mystery. Sleep well tonight, knowing you're quantum, knowing you're interconnected, knowing you're part of something far larger and stranger than everyday experience suggests. Let the quantum uncertainty be your lullaby. Let the wave functions collapse gently around you. Let the mystery hold you as you drift into dreams. Good night. May your sleep be peaceful, your dreams be quantum, and your tomorrow be filled with wonder at this strange, beautiful universe we share. Until next time, this is your Gentle Scientist signing off. Rest well.